Can you hear me? Okay, so let us start this afternoon session. I hope everybody is well caffeinated. So our first speaker in this session is Professor Abdullah Shams bin Tariq from Rajshahi University, and he's going to speak about non-monotonic nuclear potentials from energy density functional methods. আমি আপনাকে 20 মিনিট পরে আমি একটা টাইম ওয়ার্নিং দিব হ্যাঁ
So thank you very much for this opportunity and honor. I would like to start, as this is a celebration of the legacy of Dhaka as well. So two illustrious people with connections with the University of Dhaka and the Department of Physics. One is Fazle Bari Malik, who studied here, but then he went abroad. He did his PhD under Heisenberg, and then he basically settled in the US. So he has actually, he was a bit like, he used to say that his Heisenberg would have like many divisions in front of him. So one in atomic physics, one in condensed matter, one, he would like to do many things. And Fazle Bari Malik was a bit like that. So he also did many things. I think in the West he earned his name. But the second name, Hiranmoy Sengupta, is one who is perhaps an unsung hero of the University of Dhaka. I've always heard high words of him, of praise from his colleagues, but he has kind of never been celebrated. And I would, because my first, may I just mention that I remember going to the ICTP and meeting Marilena Avrigiano, who is one of the top names in nuclear reactions or nuclear in the world. And when she saw in one of our papers that Hiranmoy sir was our co-author, he said, "Oh, Sengupta, he is famous." I mean, can you or can we think of another Bangladeshi scientist who would meet the same expression from a colleague in the same research area, that he is famous in the world at a global stage? I'm not so sure, but this was the stature of Professor Sengupta in the eyes of his peers around the world. So I would like to dedicate this talk to Professor Malik and Professor Sengupta. They were both extraordinary human beings as well. My co-authors for this talk is, first of all, I would like to talk about Arun Bosak. Arun Bosak sir is another person who is, now people know about him, but he has remained in Rajshahi for a long time and really not that celebrated. But he is also a great figure, and he is the father of this discipline, this field of research there. And Sujon Islam is our kind of currently leading the work there. I should, of course, also mention Shushanto Dash, Nure Alam Abdullah, and Sakhawat Hussain, who in their times, they gave a big boost to this work, to the work that I'm going to talk about. Here are some other, mostly students, and I think I missed Raziul Islam, who is here, who is attending, but he's also one of them who worked with us. And here are some foreign collaborators and some other teachers. Two of them, Shamsher Ali sir and Nurul Huda. Nurul Huda, he spoke this morning, and Shamsher Ali sir also has connections with Dhaka. He taught here, but they contributed a little bit in their times. But so Actually, when I chose this topic, I was thinking of in the earlier announcements of this conference, there was a mention of many body systems and a statistical system, many body systems. There was nothing that could quite go towards particle physics or something. So I thought maybe it's a good opportunity, or maybe it makes sense to talk about nuclear physics or the work that has been done in Rajshahi in nuclear physics in Professor Boschak's group. So nuclear physics is actually neither few body like particle physics, and it is neither many body like condensed matter. It's difficult to handle actually. You have complicated models, shell model, collective models. These are models, but still they give approximate results. They are not, and in fact, I feel kind of sorry because I had my time in nuclear physics and also in particle physics. People always think of high energy physics as more glamorous, and nuclear physics has been kind of abandoned in some way. When people have abandoned it in some way, I mean, some parts, hadronic physics or nuclear astrophysics, are still a little bit fashionable, but there are very interesting problems and very interesting things that have been kind of abandoned because it's you have to work with the way the world is moving to get positions, to get studentships, to get teaching positions, everything. There are many issues. So the continuum limit, or the continuum or the many-body limit exists in nuclear physics in very exotic places like neutron stars. So if you go into neutron stars, you get really a many-body nuclear system. But finite nuclei are not quite many-body, though we will try to apply a many-body method here. So the energy density functional formalism, the basic thing is quite simple. The total energy of a system is expressed as an integral over the local energy density. So you somehow have to find out, that's the theoretical work. You get to an expression of how the local energy depends on density. And then this density is a function of position. So if we know that we know density distributions of nuclear matter, but if we can express the energy of nuclear matter, the local energy density of nuclear matter in terms of this density, then we can integrate over it to get the system, to get the energy of the system. Actually, it's exactly this equation or this that is being used by the DFT people in condensed matter or chemistry. It's used a lot there for many electron systems, but not so much in nuclear physics. But there is a nuclear density functional functional group, section or sub-discipline which is around. So Keith Bruckner and his collaborators, they actually reached this expression, and this is, I for a long while I thought this came after Kohn and Sham, or Hohenberg and Kohn, when they did their density functionals. But no, actually this was before. I mean, Kohn and Sham, the equation is 1965, but this was a parallel development. Bruckner started much earlier, and it went the whole 60s. He was writing paper after paper after paper, developing this, and it's quite a testament to the greatness of Bruckner himself. So he and his collaborators, eventually they reached this expression for the local energy density of nuclear matter, and then there are tweaks here and there so the last term, for example, is the finite correction, so finite volume correction, because it's not infinite nuclear matter, so you need to do some correction. The last but one term is the Pauli effect correction for the Coulomb part, but something like that. You arrive somewhere and then you make corrections. So this is the building block. This is what the kernel that you integrate upon. And then there is another element is the sudden approximation. So in the sudden approximation, we assume that there is no time to rearrange, and the densities simply add up. In fact, this also leads to a situation where the density goes above the saturation density. nuclear saturation is, because nuclear matter is saturated, and when you overlap quickly, there you get something. And as opposed to the adiabatic approximation, where you have a maximum saturation density, this gives different results. So if you look here, the potential goes monotonically down, which is the usual thing that we usually know. That's in the adiabatic approximation. But in the sudden approximation, when you try to overlap, you get a repulsion. So we have there is a repulsive core, which is kind of a key to what we will all be talking about. So the typical potential between two light nuclei, as we have read in textbooks, is that the nuclear force follows the nuclear matter distribution. Because nuclear force is short-ranged, so it has to follow the nuclear matter distribution. So it should be like this, which is a Wood-Saxon form, familiar from our textbooks. It's deep and monotonic. These two terms are to be remembered because the potential we will be talking about is not deep and it's not monotonic. This is what it's like. This is here it's referred to as molecular. We were first calling it molecular, but then for some reasons we switched to non-monotonic to be more general, because molecular potential has a repulsive core, and this is standard deep. This is a squared Wood-Saxon form. That's why you don't get the Wood-Saxon type behavior. But it's a deep monotonic potential, and the shallow non-monotonic potential is very different from that. It has a short-range repulsion, and it's very shallow. The significance of this repulsive core is that for small separations, that is large overlap, when the nuclei overlap very much, then it accounts for Pauli exclusion effects. So the repulsive core doesn't allow you to overlap. At short range, you get a repulsion. And unless dealt with in this way, what people have been doing, because there are problems and they have been dealt with, so they take care of it in less elegant manners. You put in something by hand, you put in a repulsion by hand, or you put in some kind of normalization. You normalize your data by a factor of 0.9, whatever. It's an empirical normalization. You fit the data doesn't fit. You just put multiply it by 0.9 or 0.7 or 1.3, and you get a fit. So these are not elegant manners, but this is more based on theoretic, with a firm theoretical underpinning. So you start from the nuclear density and you calculate. So this was the first paper in this work, and this was, I'm happy to say, this was my master's thesis, my master's project. This was elastic scattering. Here we were looking at, this was the first time when Professor Boschak came back from US with after discussion with Professor Malik, and we were trying to and he gave me this problem, what can we do with this? And we found out that for elastic scattering, we can do equally well, as good as the standard potential. The non-monotonic potential works equally well. But then, if you notice, I mean, elastic scattering is a surface phenomenon. If this was the potential I was showing you just a short while ago, and this is a notch test result. So it's like you put a notch on the potential somewhere and see how it changes. And you see that it's most sensitive, the scattering is most sensitive to this area, which is where the two potentials are very similar. So you can't differentiate between these two potentials by looking at a process that depends here. But you need to look at processes that are sensitive to the nuclear interior. So that's why we needed to look at processes that are more sensitive to the nuclear interior. And that is, so we started with nuclear transfer reactions. So one nucleon transfer, alpha T, you can see that it's starting to look better. This fit looks better than this one. Large angles, you get the pickup that is needed. And then as you go to 2 and 3 nucleon reactions, you can really see how it improves a lot. It's getting significantly better. I don't have time to show this figure for a long time, but I can assure you that if you're not very impressed with the fits, I mean, nuclear reaction fits are often much worse. I mean, it's getting to this level is actually quite good. And this was a big thing to happen. It was like back-to-back papers accepted. So you can see that they are the same date, same issue. The first one and then the second one, they were published on back-to-back in Physical Review C. So then we go on to alpha P, as I was mentioning. Alpha P, it really gets big. You can see the difference very clearly. This is this is the prediction that you get from deep potentials, but then they normalize it with the factor and then try to fit it here. But this is what you get directly from our non-monotonic potential that we get from EDF. So this was a big boost for us that we could do this, truly better. And now, then there were other areas. We started exploring. There was inelastic scattering. And then this was another area, polarization data. So these are called vector analyzing and tensor analyzing powers. And if you compare this with the fits that exist in the literature, this is way better. So significantly better fits to polarization data as well. And then there was this issue of the Goldberg criteria. Goldberg criteria is how to differentiate between two potentials. Because two potentials with different depths produce the same phase shifts. As I said, in elastic scattering, it's a surface phenomenon. So two potentials, even if they're deeper, a deeper potential will just have extra nodes inside the potential, but outside the asymptotic behavior is the same. So this was a work by Bay, who derived a transformation. So you start with this potential, a deep potential, and you transform it. He called it supersymmetric transformations, but it's nothing to do with the supersymmetry of particle physics. But you transform this and you reach these potentials. So these are phase equivalent potentials. So you can start with a deep potential, but you can get a phase equivalent shallow potential with a repulsive core. And this is where they compare the standard potential of Buck, Frederick, and Wheatley with the potential of Ali and Bodmer. Here again is perhaps some of you wonder why Shamsher Ali is rather well known. It is because of this work. Ali Bodmer this was his PhD work. So the Ali Bodmer potential is still considered quite standard, and so they compare and it matches. So, but this was the transformation from deep to shallow. So now, so this is what we realized, that this is what I was saying a little short while ago, that you see the phase shifts, the wave function is the same outside. Inside the nuclear potential, you get, if I could zoom this, then you would see that the blue lines have just more nodes inside. Outside, they are the same. Here again, the blue lines have the one with the deeper potential has the wave function just has more nodes, but the asymptotic behavior is the same. So one needs to go. So what Goldberg and Smith said is that we need to go to high enough energies to observe an exponential fall off in the angular distribution. So if you look at these are typical angular distributions that we deal with, and like I showed you in our first paper, these are angular distributions that go like this. They are Fraunhofer all the way. But if you, or there are some Fresnel effects here as well. But if you go further to higher energies, you see angular distributions that look like this, that just simply fall off sharply. So the first thing is that we need to go to higher energies. The second thing is we need to the data has to extend to a particular angle. There is a critical angle called the Goldberg angle that if data goes beyond that, then that data can be fitted only with one potential, not with many. You no longer have the freedom to choose to many potentials. So this was a later work that we did more recently, done mostly driven by Sujon again, where you see many many potentials at lower energies. This is the real volume integral, so kind of measures the strength, the potential strength. So you get many families at lower energies, but once you reach the Goldberg criteria, then there's only one family that survives, and that happens to be the one dictated by EDF. So that's reassuring that, okay, this is the good family. So this we get once for oxygen-16, and then again for carbon, the same, only one family survives, and that's the one obtained from EDF. Then this is another problem, the equations of state for nuclear matter. Equation of state is this binding energy against density curve, which is, so there is a connection between this and this. So for different values of incompressibility of nuclear matter, so incompressibility is this second derivative at this point, which basically differentiates between these different curves. So if it's a stiffer, or if it's a softer equation of state, or if it's a stiffer equation of state, depending on this, we get different potentials. So we can actually correlate between, we can fit data and try to guess what's the value of K. And the incompressibility of nuclear matter is not a well-determined value. It's still not well known. So here, this is what was done, and we got a very robust estimate. And so the volume integral value is something like this, and we get a very robust estimate of the incompressibility of nuclear matter, which is 222 plus minus 5 MeV. This is, as robust as anything that you get in the literature. So then this is more recent work, as you can see that this is just submitted. This is about fusion cross sections. So that is, the fusion cross section data is well described here, but what you cannot see in the fusion cross section data is more available, more easily noticeable when you plot it as the S factor. The S factor is a way to plot it where you kind of bring out the nuclear effects for fusion. And here, the S factor, this is the kind of classical or the well-known Cochran and Fowler curve, which shows a monotonic increase at lower energies. But if it reaches a maximum and starts coming down, this is known as hindrance, the problem of hindrance in fusion. So to address this problem of, so here with this potential, we are able to get this hindrance straight away. Anyone else who have tried to address this, they have had to done something either by hand or going a long way to deal with this. Couple channels, they are not all not sound, but they are more complicated. This is a straightforward way where we reach the hindrance. So we can reproduce fusion cross sections, and we can reproduce hindrance, and we can describe hindrance. This is another work this is not even submitted yet. This is work under progress, but another polarization curve, which actually is very impressive. If you look into the fits in the literature, they are, absolutely nowhere near this. So this is the series of work that has led to this. And as I said, this is not, I don't claim credit for this. I was part of the group, but this is, I would say, more of Professor Boschak and his team, the group there, what has been done there. And there are other groups, actually, a few other groups. It's still not standard, but the top in Misichu and Esbenson are in Argon. The second group is in Ukraine. The third group is in Iran. And there are a few isolated papers. There's one group from Punjab University who wrote a paper, and another one. So a few people have been reaching the same conclusion, but still the standard is that the light nucleus potential is deep and monotonic, follows the Wood-Saxon form or something like that. So to summarize, there are great successes, but still not recognized as the standard. We are still not recognized as the standard. There was a time when it was very difficult. I mean, APS journals were very difficult. They were with very harsh reviews. We were being rejected, but then now we are back there. So it's still not recognized as the standard, but if one day it is, some books will need a little bit of rewriting. So the EDF formalism, in summary, is found to be a powerful tool for nuclear physics as well. It's not density functionals. It's not only for condensed matter chemistry. You can use density functional methods for nuclear physics. And no matter what, this will remain a legacy of Professor Arun Kumar Bashak and the University of Rajshahi. Thank you.
So are there any questions?
I actually have one question. This data that you are actually trying to fit, what's the energy at which these are being measured, the measured energy levels?
The energy is tens of MeVs going up to hundreds of MeVs or even 1,000 MeV. But GeV. But for the astrophysically significant work, that's at the end. These are just a few MeV. So single-digit MeV. So astrophysically, though the fusion cross-section at low energies, actually I forgot to mention that those are experimentally inaccessible energies. You cannot do fusion reactions at those energies in the labs. So it's important to get some theoretical estimate. And they are very important for nucleosynthesis as well, those energies. So the energies here,
Sorry. Can I ask one question?
Yeah.
I am a little bit surprised. This is kudos to your work. It's just that usually when you think of this density functional formalism, right, in case of condensed matter, when you have a system, then you're dealing with degrees of freedom, which is 10 to the power 23, etc. Mm-hmm. But if you're thinking the nucleonic picture, then it is not what you'd call a large system.
Yes, of course.
It is almost on the verge of what we call stochastic thermodynamics. Mm-hmm. Things are fluctuating in domination.
Yes, exactly.
And still, this framework actually seems to be dual. Is there any rational explanation behind this?
No, it's one is that in the local energy density, there is this finite volume correction. So you have to look into that paper by Bruckner and others to see what they have done and how that deals with finite volume. So instead of an infinite nuclear matter, they talk about what happens if you have a finite volume.
It includes things like surface effects, all this kind of thing.
Yes, I guess so, yes.
But if you think in terms of, let's say, the fundamental theory beneath is, after all, is QCD, right? So is there any explanation that has been sought in terms of the fundamental theory? You can write always in terms of like some, as we do in Carrel-Lagrange, things like that instead of QCD you can do. But is there any bridge that has been developed?
Well, bridging QCD and nuclear physics is another interest of myself, but it's like QCD directly to many body nuclear physics is quite a long way. We are, the progress that is going on now is trying to do like nucleon scattering from QCD, and there are people doing this on the lattice and otherwise as well. So for nucleon phase shifts, nucleon scattering or small systems, people are trying to doing this from QCD. But few body nuclear physics is, I think, still a long way away. Yes, sir.
I think I can give a partial answer to that, perhaps. So something like 50 years ago, there was a potential developed called the Skirm potential. And that basically comes from Bruckner theory and the Bethe-Goldstone equation. And it is something that fits the properties of small nuclei, medium nuclei, reasonably well. So actually, I'm a little surprised that you're using this potential rather than the SCRM potential. Is there
Okay.
some reason for
No,
that? Because after all, this does have some theoretical underpinning.
No, I mean, the SCRM, it's a matter of what you use as the, so it's, if you look at the expression for the energy, local energy density, so there is this kernel, in the kernel, there is this term, which is the V term here. This is the nucleon-nucleon interaction. So I mean, people have been using, in here, there are people who use the SCRM potential. So you can do the same thing with SCRM and get similar results. And there are people who are doing it, who have done it.
Yes, but that's got the additional validation that it gets you the energy levels of light nuclei right, correct. So that is, I think, the potential of choice.
Okay, I mean, for us, it's more historical that we didn't go to SCRM. We started this before we came to know about. But I mean, I think successes of the SCRM potential are still limited. I mean, it's not that SCRM is very widely accepted. You are very correct in saying that there was a lot of promise and a bit of hype about it, but I don't think it is still getting anywhere near the standard. So there are a few people who use SCRM potential, and but not many.
Okay, if there aren't any more questions, let's thank our speaker. So our next speaker is Gopi Chandra Kafle, and he is from Tribhuvan University in Nepal, and he will be speaking about exploring electronic and magnetic properties of pristine, strained, and defected MX scenes.
Okay, thank you, the organizer committee, especially Kamrul and the Supriya ma'am and whole team for this opportunity. Today, I'm going to discuss about the electronic and magnetic properties of the pristine systems and defected system in MX scenes. Actually, these this is my actually my lab where I'm working within in the Tribhuvan University, Nepal. This is my MSc student is working in this field. These are my collaborators from the Nepal and abroad, Nepal, India, and abroad. Basically, we are doing this molecular dynamics work. Then ABO3 types of materials and the 2D types of material, and somehow magnetism and somehow water splitting and experiment and theory persons with some collaborations. Basically, this work is based on these people's 2, 1, 2, and 3 peoples. They are my MSc students, and is my collaborators. Collaboration, they are other my groups. These topics, outline of my topics is this one, introduction and motivations, the theoretical and computational details, not details, and simply these computationals. Then TI2 maxines, TI2 and maxines, formation of TI2 maxines, and its derivative and functionalizations with F, O, OH, and H, and with the strain effect on the electronic and magnetic properties, then vacancy and the doping effect within the TI2N systems, and then conclusion. Actually, max phase. Maxines is derived from the max phase. That is, max phase are there as various kind of max phase. This is the A. This is MX, and this is A layers and max layer. And this the main formula of max phase is Mn plus 1 AX, N plus 1 AX. That Ma bonds are actually that Ma bonds are very weaker than that of the N bonds. So Ma bonds are weaker than the N bonds. So when we are etching the process, after etching, then A layer can easily be removed. So it becomes the maxins. Actually, these maxins then because when Mn plus 1 AXN phase Xn, when we remove that A, and it becomes Mn plus 1 Xn types of the system that is called as the maxin. These are the example of 211, 312, 211, 312, 413, and 514 types of the maxins. There are various types of maxins. This is the experimental etching process. This is not mine because we are doing the theoretical one. So after etching the distant A layers, it becomes in M2X phase becomes M2X, and M3AX2 becomes M3X2, and so on. So I'm focusing within the this M2X type of phase, M2X type of phase, because it has the various kind of applications from spin-tronics devices to future generation technologies. To the water splitting and various purposes, even in the agricultures and others. So it is very important to this in maxins because it is the world of the 2D materials. Because when we are looking forward from the global 2D market point of view, this in global markets of the this in 2D maxins is going to increase from 2.30 billion to 3.34 billion in 2033. From this year to 2033. So it is very important because it has the very important in the case of the energy conservation to the energy conservation to the chemical defects, chemical drug delivery to the various kind of applications. Basically, for this we use pseudo-potential approach, density function theory. For that we use the quantum espresso. In the quantum espresso, it generally works within the when the works. It is very best for beyond the RC. It is very good approximation. So we use it. And here in the energy functional, we use GGA plus somehow U, and sometimes we use the SOC spin orbit coupling and some HSE 06 also we use sometimes because of to check the our validity as well as the with experimental results. So this is the formula to find out because to know whether this material is stable or not, we have to do the following three things. One thing is there should be the structurally stable. That material should be structurally stable. And the second one is that should be the chemically stable. And third one, that should be dynamical, should be stable. That for the structural stability, we'll go towards the energy minimization process. And the energy minimization process is done by this, by taking the density, by taking the first density. And then after we'll go to the cell consistency approach, then we'll calculate the energy, then the energy versus lattice parameter. When we calculate it, then we'll get the energy structure, minimization, that energy structure stability. Then for the chemical stability or thermodynamical stability, we'll go towards the formation and cohesive energy calculations. And for the dynamic stability, we go towards the phonon dispersion relations. Okay, this is the case. This is the formation energy and cohesive energy. And in the formation and cohesive energy cases, here bulk is the bulk structure of material. In isolated means single atoms calculations. Other are single vacancy defect and the single add atoms defect also we have calculated. Okay, then we use the quantum equation, no doubt. Quantum equation we solve. After solving the quantum equation, we'll get the particular kind of whatever we need, density, state, energy, and others. Okay, for that, this is the max phase of Ti to N. First, we take the Ti to ALN. Then after we each we taken out the there's an A layer. After taking out the A layer, it becomes Ti2N. That is the maxins which actually we want. And this is the top view of this is the side view, and this is the top view of maxin. This one is the A1 is the max phase, mx2 m2x, and A layer m2x, A layer, and m2x. In order to get the m2x layers, we remove this one A layers. So we remove it, and after that we use this one the pristine types of maxins. But there is the when we are go to ask to make the instrument or to make this particular kind of miniaturization process, there may be the leakage of currents, leakage of charges, and various things. So to remove these ones, we have to go first of all passivations. First of all, we have to go to passivations. So after before that, means whether this material is stable or not. For this, we check out this one the Ti2N, pristine one, and the functionalization one. After these ones, then we observe these values. These values which are in the parentheses are either experimental or previously calculated values. So after calculation, we came to conclude that our material is very stable one. This Ti2N is stable, and other also stable Ti2N-F2, Ti2N-O2, all are the stable one. But when we are looking the very carefully, and the Ti bonds between the this one Ti2NO2 is very stronger very larger than that of the others. And after that, when the structure stability shows, this one, the structure stability shows that this is very close resemblance with the experimental and other calculated values. So our calculation is going in the right track. We can say in that way. And after calculating the Quasi-band Fermi energy of the systems, then Quasi-band Fermi energy systems goes like this way. Here Ti2NO2 is that is most stable. In the case of where this one is Quasi energy. And in the case of the Fermi energy, we say both Ti2, F2 and Ti2NO2 are more stable than that of the other one. While calculating this one structural property and others, we first make into mind that whether these materials are magnetic or non-magnetic. For that, we use first non-magnetic systems, and second one is ferromagnetic system, and third one is anti-ferromagnetic systems. After calculating what we'll get, this one's anti-magnetic means ferromagnetic M2X is more stable than that of the anti-ferromagnetic and the non-magnetic. So we use the ferromagnetic types of Ti2N, because in case of the ferromagnetic Ti2Ns, we observe this type of band gap. Okay, this is the without using the spin orbit coupling and with spin orbit coupling with. But we observe here just near to the Fermi level, there we see the crossing of the bands, and similar, for example, in A, and similar kind of scenario is observed within below and just above the Fermi level, very few below and above the Fermi level. So this is the ABCD. ABCD is named as ABCD, and this is ABCD is just like the Dirac one, because MX2 is just like the graphene type. So it shows just the Dirac like ones. This red line, the dotted line is Fermi energy. But when after using the SOC, we observe that Dirac line cone is slightly opens. It means MX actually max phase already found in the non-magnetic materials. The MX2 in the ferromagnetic materials, and their band gap, then some crossing of the band gap is arising. It means what? It also gives some kind of feature of topological properties. But our aim is not to go towards the topological, to find out the topological insulating, because here we want to discuss how our material is BFs, when the stain used and the doping used and vacancy after using the vacancy. Okay, this is the case. Here is the without using the SOC, and here using the SOC. When using the SOC, what happens? It opens the topological non-trivial gap. It opens the gap I and II. It opens the gap after using the spin orbit coupling. This is mainly due to that band inversion. Band inversion occurs. First and second, there is the inversion of band also. That inversion of band is due to the hybridization of dxy from the T2G orbitals and dg square from the EG orbitals. Okay, and there is the inset. There is some band open is clearly seen in the inset. Okay, then when again after using the this one properties of whether this ferromagnetism or on another one property, we use Ti2 ALN. This is max space. And then first this one is the one of the max space. Another one is Ti2 and F2 F2 functionalizations. Then another one is Ti2 NS2 S2 functionalization, and other one is OS functionalization. And below one is O2 functionalizations. And we observe that max phase reveals that considerable metallic character. And similarly, the presence of SOC doesn't influence the outcomes because it is the non-magnetic materials. One is the non-magnetic materials, there is less effect on the spin orbit coupling. So electronic property of Ti2 F2, Ti2 NOS that are similar to the presence of the electrophile minus F minus OH, which accept actually the one electrons from the Ti. Similarly, O is the O electrophile actually which accept the two electrons from the Ti atom. So it is that charge carriers correspond to direct ones that behaves like whole packet. And whole packet and electron packet, out of them, they behaves like the whole packet. The oxygen termination convert this weakly half metallic to 100% spin polarization in the half metallic case. Spin polarization, that is half metallic case. This is observed from the here. This is Ti2An. This is in the Ti2An. This is weakly half metallic. With half metallic behavior is observed. This is the scenario of one is using SOC, and after using SOC, that half metallic property slightly increases. Okay, similar kind of condition when you are using the this one spin up and spin down, and sometimes whether it supports to the HSE calculation or not. So we use this one GGA calculation as well as the HSE calculations, where we observe dx2, dxy, and dx square minus y square that, and dxz and yz that state from the separate degenerate states. We observe from the this is density states. And here these density states is not straight lines. It is because we are using the tetragonal integration here, not in the Gaussian smearing. It is tetragonal smearing. So it shows, because tetragonal smearing shows the very accurate band gap. So to use this one, we use that in tetragonal types of smearing. And that there are non-degenerate DG that state dominates in the both spin channels. So in the breakdown of T2G and EG states due to the local symmetry, that is responsible for the half metallic in Ti2 NO2. The top and bottom layer of Ti provides actually 2 electrons from the O atoms, 2 electrons from the O atoms. There is the splitting of bands. 2 electrons from the O atoms jointly provides the 3 electrons from the neighboring N atoms. Because so in the when it combined with the nitrogen, it is plus 3D is 3 oxidation state, and when it combined with the oxygen, it gives the plus 4 types of states. So magnetic remaining the 3D 1 electrons that remains out of them in order to complete the 8 octet. The remaining 3 electrons is removed, that either fills the non-bonding state or helps to delocalize the systems, which provides the magnetic moment, that magnetic feature, that is 0.27 μV for the titanium atoms. And that magnetic moment splits the states into the fully occupied bands, that majority spin channels, and open the band of the minority spin states, providing the semiconducting nature in the spin down channel. It is easily shown in the semiconducting nature in the spin down channel. Here, this one, blue one and red one in the upper side, these are the these overlap with each other. So out of 5, we see only the 3 out of 1, 2, 3 out of 4, we see only the 3 bands here. Similarly, when we are using the strain, and we want to see what happens when the strain is used within the systems. After using the strain, We observe here, this is the strain-free systems. We got here the half metallic behavior. Up spin channel shows the metallic and down spin channel shows the half metallic types of behavior. When strain used, after using the when strain used in the means in the TI2N, TI2FN, and then OHN shows the same kind of physics. So we no need to go towards the these systems. So we went towards the TI2NOT systems. When in TI2NOT, when we are using the compressive strain from 1 to plus 5, that compression plus 5 up to 5% compressions, we observe that this one spin down channels, the band is moving towards the balance band, and this spin down channels slightly move towards the conduction band. So it shows the non-magnetic behavior. So it converts, actually on the compressions, a system converts, in the compression system converts the non-magnetic behavior, non-magnetic metallic to metallic behavior. Because it is the non-magnetic, this is the metallic half magnetic to antiferromagnetic conductor, antiferromagnetic conductor types. And when, but after compression, there is no effect in the half metallicity. There is no effect in the half metallicity of the systems. This is the case when we are using the biaxial strain within the city. Biaxial strain means in X and Y plane. This is 2D dimensions. So we use the biaxial types of strain here. This is the 5%. This is the case of the 5% compression and the 5% tensile spring. This is the band structure plots, and this is the density of states plots. Then this shows the same kind of features. In 5% compression, it shows the spin down, spin up channels. That is the half metallic types of behavior it shows. But means compression, there is the compression. There is the in compression there is non-magnetic types of behavior it observes, and metallic characters it crosses the bands, so it is non-magnetic, non-metallic. So there is no use of spin up and spin down channels, effect of spin up and spin down channels. Similarly, when after using the 5% that tensile, we observe this one. That band is crossing with each other. Where spin down channel shows the particular band gap, but spin up channel, this red one, so crossing the band, which means it shows the half metallic characters. Similarly, when using the vacancy defect, this is the strain one, and after using the vacancy defect, we also using the vacancy defect, we use the for the structural stability, we use that formula, previous formula, whatever we discussed in the methodology sections. There we observe this one. This is the 25% N vacancy. This is the 12.5% TI vacancy, and here is some 12.5% O vacancy, oxygen vacancy. Here is the we use 3x3 supercell to make the concentration of TI more less. That is 5%, 5 kind of vacancy defects. So we observe all the systems, all the downstate property of all systems are the non-magnetic in nature. Then after means when we are seeing the single backbone formation energy structures, that shows vacancy, TI vacancy is more stable than that of the other one, but all systems are unstable in nature. It is mainly due to the TI requires the 6.2 brick, the TI-N and the 3 TI-O bonds, and because 3 TI-3D bond and O2P overlaps, which gives the 4 oxidation state as same as previous one, and so TI-O bond is relatively stronger than that of the TI-N bonds, because when TI D orbitals mix with the means oxidation, we mix with this one, it fulfills the +3 oxidation state. oxidation states, okay, same kind of behavior is observed. So when we are using the 12.5% Ti atoms, Ti to NO2, everybody changes the electronic property from half metallic to the semiconducting behavior, half metallic to they are the semiconducting behavior. It shows the semiconducting behavior, and that semiconducting band gap is 1.72. It is very significant, and it is close to 2. So it also can be used for the water splitting as well, and other kind of spin tonic devices. When concentrations increase, it decreases that 5.5%, then we observe this one is slightly weak metallic one. There is weak kind of metallic, weak half metallic we can say. Okay, that's a semiconductor we can say. Semiconductor found in TI defects. The conduction band near the Fermi limits are mainly dominated by TID. Otherwise, if we look here in the 12.5 systems, in the conduction in the conduction bands, their TI3D are dominated. In the valence bands, N2P and the O2P are dominated one. So due to the effect of this one, and when they are combined, it gives the half metallic types of behavior. Similarly, when O and N vacancy, and N vacancy, we observe the same kind of behavior. In the O 12.5% defects, the bottom of the bands are mainly dominated by N2P and 2OP states, the conduction band by the TI3D states. Similar shifting of Fermi level towards the unoccupied state, forming topological Fermi metals, topological types of Fermi levels, because certain band opening when using the SOC and when you with and without types of SOC, and two distinct like ones are observed in the C and D, revealing that P and N type of dropping characters, that B becomes more distorted, which diminishes the quantum oscillations. In N25, below 1 is the N25, 25% defects, same as that of the O defects, that applying the strength of the associated TI atoms, the band gets slightly splitted and open up 0.01 electron volt more. Okay, similarly, when we are using when doping concentration on chromium, manganese, and the cobalt doping in Ti2 NO2, we observe CRO, when chromium dops, when CRO bands elongates and CR bands the compression, which significantly influence the electronic and magnetic properties of the that system. Similar in case of the Mn dopant, the same behavior is found. Slightly variation in the bond length. There is no change in the Mn doping, but in case of the coal doping, the bond length also elongates, and the compared to that elongates and shorter compared to TiO and Ti2 in the pristine case. So results of chromium are slightly shifted towards the bottom side. And when we are calculating the Fermi synergy, the all system is found to be stable in nature. So we went towards the different calculations after Mn after doping this one Mn in Ti2 to allows the 100% spin polarization half metallic to weakly semi-metallic nature, half metallic to weakly semi-metallic in nature. Now the intrinsic magnetic moment of Mn 3.73 μV, which is actually Mn reduces after doping that Mn that reduces the magnetic moment Ti by 2. Very few. It reduces, and these are the band structure of the chromium doping, and then chromium doping transform the half metallic ferromagnetic to half metallic antiferromagnetic case, half metallic ferromagnetic, half metallic antiferromagnetic. But here, if we observe very closely, anyway, it gives the antiferromagnetic as a whole. It is mainly due to the that reason, whatever we have already told previously, because it is the splitting of T2G orbitals and ODG types of orbitals of the systems. Same kind of similarly co-substitution preserves the ferromagnetic half metallic. The CO means doping preserves the half metallic ferromagnetic, and magnetic co in the Ti2 NO2 is 1.90, which diminishes the individual magnetic Ti from Ti 0.2 to slightly reduces, but no negligible values. Okay, it is the same. This is the conclusion. The formation of cohesive energy of cohesive structure stability maximums and parent max space, this one are apparently more stable than that of the other. Then well separated optical electrical branches with no imaginary phonon frequency reveals the dynamic stability of T2N. and others are the sometimes some cases it will be changes from the half metallic to metallic one, and some cases it retain the half metallic as well, which this indicate that this type of material is very useful for the useful for the spin tonic devices and future generation technology devices. And no doubt it acknowledgement goes to that conference organizing committee, especially Kamrul and Supriya ma'am and as a whole team, and the Professor Narna Adhikari, Central Department of Physics, Dhruva Podel from the AIMS Lab USA, and Yogendra Limbu, Neeraj Shah, and Alok Lal Karnat is my student. Thank you.
Questions?
Yeah, in slide 14, you showed that the spin-orbit coupling opens non-trivial topological gap.
Yeah,
So how do you know that?
okay. 14, no?
Yeah. Did you calculate the Chern number?
Yeah, this one. You look here, this one, when we are using the spin orbit, this is the case of, this is the case of without using the SOC, and after, means there is the band crossing here in I and II sectors, but after using the SOC, there is, we observe there is band opening.
No, but did you calculate the Chern number?
Yeah, we are calculating also.
More questions? Okay, if not, let's thank our speaker again.
Okay, thank you.
So our next speaker needs no introduction, at least to this audience, but I will introduce him anyway. That's Professor Arshad Moomin, and he is going to speak about infrared effects violate Landau-Young theorem.
I'll try to finish as quick as possible. I'm already too tired. I was just sleepy. Okay. Okay, I actually. Okay, fine, thanks. Everybody has been thanking the organizers. Let me not thank the organizers. The reason is very simple. Those of you might not be aware, the program to arrange this conference started a long time back. And when I realized this has actually come to a fruition, I decided to quit Dhaka University so that I don't have to actually work very hard for this conference. So I'm very much pleased to see that they have actually become successful despite my running away. So I think let us put a big hand for the organizers now. So I'm not pointing out to any particular person. I mean, the whole team actually deserves their thanks. Anyway, I think you should, I will try my best to actually make the talk as short as possible, partly because myself, I am quite tired after 4 days of listening to all this area of wonderful talk, but, brain has to actually work a lot trying to comprehend things. I was trying to comprehend most of these things, and I would say that I failed most of them rather miserably. Anyway, so this work is sort of like has a philosophy which you can summarize in 2 words: what if? Usually when you deal with quantum field theory courses, you actually assume certain symmetries. And as a consequence of this, some of these things pop up. Some of the results you get, you have heard about something called selection rules, etc. They pop up. So this had been sort of like an adventure for this work-based, the results that I'm presenting here is already published in JHEP last year. This has been done in conjunction with my supervisor, A.P. Balachandran, Manuel Azore, and Babar Qureshi from Lahore. So you have heard talks by Shinanda Banerjee and as well as from Bisharup that Higgs play a very important role. Now, one of the questions that people might ask that Higgs is a scalar field. So how do you know it's a scalar field? So this sort of questions actually originate from this theorem, which goes by the name of Landau and Young theorem.
And what we show, it's a very, very important theorem. Though there are certain violations of this for non-abelian theories, but here I will only be looking at abelian theories. This work is quite interesting from one particular point because, I mean, if you look at quantum field theory, you start with some Lagrangians, perturbation theory, etc. But behind quantum field theory, there was like this attempt by Weitmann in the late 1950s to systematize things based on certain axioms. Just like you have the postulates of quantum mechanics, quantum field theory doesn't have a set of postulates, which is actually that you can hang on to. I mean, there are some folklores, but this thing is actually been tried to put in a systematic order in two programs. One of them, I mean, I myself am not an expert on this, so I cannot tell the difference between them. So one of them happens to be constructive quantum field theory, and the other one is axiomatic quantum field theory. So somebody who's interested, this is something I'm directing towards the students. If you're interested to learn a little bit about it, my suggestion is look up in the book by Local Quantum Physics by Haag. And in my own journey of learning quantum field theory, I mean, Haag's theorem is something always shoved under the rug, something that people should be aware of. And it makes you appreciate what renormalization actually does for you. It allows you to actually avoid Haag's theorem. Anyway, so what we were actually delving into learning this AQFT thing, we came across this result that was actually shown around 1975. This is due to Frulich, Morchio, and Strocki. And we try to use the result to actually do some calculations, some practical calculations that actually has some impact in standard model or standard model like physics. Because usually when you people open up these books of AQFT, you find like this thing exists, that doesn't exist, sort of like reading math theorems. So this is our feeble attempt to actually incorporate some of the results in that domain into some practical physics. So I will try to break this discussion into 4 pieces. One is obviously, I'm not going to give a proof. I initially thought that, okay, I first need to give you a proof of this. Then I realized this will actually cause me to write more slides, and I'm a lazy person. You should realize a very important thing, that you would only try to become a theoretical physicist if you're lazy, but only lazy after a certain threshold, because we are too lazy to go to a lab, work at long hours, and you want to actually have some control over your life. So that's the reason why I became a theoretical physicist. So anyway, here is the proof that I don't want to write too many slides. So I will talk about what Landau theorem is, just really going to give you the statement and give you a very quick rundown how it is proven without giving any equations. Then I'll talk about this infrared effect, which is the thing that actually one actually has. And I will only give you in words how it causes the Lorentz symmetry violation. And because of this, you can write some interaction vertices just as a trial, but I think the result is quite generic. And what the result is, I'll just give you a plot. So that's basically what the rundown will be. No, I point this way. No? Okay, fine. So the result is actually due to Landau, and their name goes in the theorem. And the statement is the following. If you're dealing with a massive spin 1 particle, obviously it's going to be neutral. If it's a neutral massive spin 1 particle, so one such example is the Z0, and it cannot decay into pair of massless spin 1 photons. Remember, the emphasis is actually on the massive and the massless. The incoming state is a massive state, and the outgoing state happens to be massless spin 1s. So if photons actually happen to have, there are other ways to actually evade this theorem. So for example, if you have photons which have a very minuscule mass, much lighter than neutrinos, etc. I mean, I'm not too sure whether the students know how photon mass is measured. This is an exercise for you to figure out how photon mass is measured. You can only talk about an upper limit on its mass. Sorry, I forgot what I was talking about. I was talking about this theorem statement. So as a consequence of this, when you look at the decay mode of Higgs, what you call it, putative as a Higgs, you find there are 2 photon modes. So that immediately rules out the object from which the photon decay has happened is not a spin 1 particle. So it has to be a boson, So you immediately are led, either it is a spin 0 or a spin 2, okay? And there's no known massive spin 2 particles, which is fundamental. Anyway, so, but there's something rather interesting to this theorem, which happens to be, this theorem only appears because of two things. One, obviously, is the Lorentz symmetry. You want to actually you want to write down some transition amplitude. And this is where Bose comes in. The two photons you have identical, so they have to actually have a symmetry between the two photons. If you exchange them, there's a symmetry between the two outgoing photons. Once you try to write down all possible vertices, all possible terms as an expansion in your one vector going into two vectors, and you include this symmetry, you immediately say that all the terms are 0. So this is how actually you prove it. And as I've already mentioned this, that because of this, the Z0 cannot decay into two photons, and that's how you actually manage to say that Higgs is a scalar particle. Okay. However, this is a result that was actually established by this mathematical physicist, Fröhlich, Morque, and Strachey in 1975, that, it's sort of like when you think of a charge, we always think of a charge as a particle, but in the fundamental domain, if it's a fundamental particle, you cannot disentangle the electric field associated with a charge. And if you were to think of photons, and I am pretty sure you know from your discussion by Professor Kamrul Hassan earlier in the day, that the number of photons is not a conserved number, right? So how many such low energy photons that you can actually radiate? The answer happens to be infinite. I'm pretty sure Parvez is the local expert on this thing. He'll be able to fill you in on this thing. No. I don't know anything about Lowe's theorem. I know its name, but I do not know its. So don't shake your head. I'm pretty sure if I put you on the podium, you'll be able to actually, detail it out. Anyway, so this is the result that people had. And one of the important things that they showed, that because of this cloud of infrared particles, you immediately find that when you want to define a mass, usually actually when you write a particle, what's a particle? You actually pick up representations of Poincare group, which is labeled by a mass and a spin. But if you allow for this long-range fields to exist, this is sort of related to the thing that what Ashok was saying earlier, that there is like soft theorems. These things are all connected, but however, my knowledge is quite limited. I only worked on a particular domain, so I do not know how to actually connect it to the work. I actually had a little chat with him earlier in the day, yesterday, and it really warrants some kind of study on this thing. What's the connection between this framework and that framework? Anyway, so what you find that the punchline is you do not have Lorentz symmetry. It is broken, and that too it is spontaneously. Now remember a very important thing. If you have a spontaneous symmetry breaking, it means you have degenerate vacua. There's not a unique vacua. So the upshot of all this work was that, this I think is skipped because I've already talked about it, is that you do not have very much well-defined fields. But that is not to say that you cannot do anything. You have to actually give up something for the price of this violation of the spontaneous symmetry breaking. So to do this, you have to go back and look at the classic work by Wigner. So Wigner had classified what the representations of the Poincare group was. And there is this set that he found, which he labeled as what we call a continuous spin particles. There's no, you typically think of spins as 0, 1, half, 3, half quantized. But there's a representation for which the spin operator actually has a continuous eigenvalues. The upshot of this thing is, unfortunately, if you want to write a local field for it, it does not exist. So the question is, what sort of field would you need to write? This was this result that I mentioned. There's no local field. This was again a result in AQFT that was shown by Ingvason around 1970s. So these are very old results and very rigorously proven. But unfortunately, when standard model comes and has all this plethora of results, you tend to actually shove things behind, sort of like what Tariq was complaining earlier, that nuclear physics has lost the glamour because people think it's not interesting anymore. But there are interesting results that is over there, as I learned it myself, just few months back. And what you find that you can write local fields, but not everywhere. So if you want to define over a space slice, all you have to do is you have to strike out a thin strip. So in other words, I should have actually, I had a slide for it, but I did not incorporate in here. But you can see, I will wave my hands and you can realize what I'm trying to say. So if you have a plain sheet and you put a charge, you want to write a continuous spin field, then what you can do, you cannot write it everywhere on this two-dimensional plane. So you take the charge, draw a line, stretch it out all the way to infinity, and the moment you do it, it's sort of like a branch cut, those of you who done complex analysis. Away from the branch cut, everywhere else, the field is well defined. So this is what people in that literature, they call fields localized on a cone. And this is also related to what Sumatira was talking about. Anyons actually fall into this category as well. But here, the anyons do not have this line. To exclude this line, you actually have to take it out of the plane. That's how you actually manage to get it done. Okay, so the problem was that if I want to write a field theory for these objects, how to do this? And this is where a recent work by Moon, Rehren, and Schroer actually came into being. So they found out, this is an old result, and this is the idea actually originally comes from Dirac and Mandelstam. So what you do the following. You are familiar with Wilson line operators. What is a Wilson line operator? Is just think of a flux tube. Okay, but we'll not think of fluxes. All I will do, I will take the vector gauge field, electromagnetic field, and I will integrate it along that line that I was talking about. This object has, under a gauge transformation, a covariant way of transforming. This is a standard exercise that you actually have in quantum field theory. But the result that these people show that this Wilson line, when you multiply this in front of a charge field, this actually attaches this long wavelength, this infrared photons that we had been talking about. It dresses the charged particle with that. This is how you take it out. You can dress or undress. It's sort of like I'm putting on a shirt. You see me with a shirt, but it is only my family sees me in a Genji or something like the vest, right? So when you try to identify objects, you can identify in different manners. So if you want to put an infrared field dressed up, you multiply with the Wilson line factor. That's how you do it. Okay? And what it does, if you think it like a quantum operator, remember there's an A field up here. So A field you quantize in terms of, those of you who know a little bit of quantum field theory. Any quantum field theory can be expanded in terms of creation and destruction operators. What it creates and destroys, that's a secondary question. What's the particle that there are questions. As long as you have point credit symmetry, you can define particle. Once you lose it, then, you know what you're talking about. This is actually, very well, some of you already know that this is intimately connected with Hawking radiation. The interpretation of Hawking radiation when it came up. Anyway, so this creates a charge where you are, and remember that I was talking about this flux tube. The flux actually has to escape somewhere. It is escaping out at infinity. But this is how the construction actually goes about. Sorry, forgot to shut it down. Oh, all right. So this thing is actually known as what they call a Scott field. So the point is, I'm sorry, I think I skipped. Right. Okay, so if you want to have a Z naught going to 2 photons, remember the Z naught is created usually by annihilating a fermion and antifermion. So this is Z naught itself does not carry a charge, but it is created out of some pair of charges. So therefore those charged particles will be dressed by these infra fields. It is sort of like, this is an analogy that you have, that a charged particle you might not detect, but it is sort of like when you put a perfume and walk out of the room, the perfume lingers. So the charged particle might be gone, but You do not see the charge particle inside a detector, but the charge particle leaves an infrared field, which is actually created by this puncture. Remember, this is actually extends all the way to infinity. So, since will have two charge particles, I will have to dress each of them with these two Wilson line operators. Now, what happens, you may remember I had mentioned, how much time? Okay, I think I'll be able to make it because I'm not going to give you the calculational details. So the idea is that, if you want to actually have a well-defined operator, those are fairly brushed with a little bit of scalar field theory quantization, you have to normal order it. So therefore, I will have to normal order the operator I wrote down, and that phi that I have written over there actually is nothing, but you notice in this is just that exponential of a dot with a vector that extends, I integrate along the line, you take the tangent vector. And now the interesting thing is, this has to be a space-like vector. There's a reason why I'm actually doing it. Because you remember that if you try to quantize photons, photon being a vector field has negative norm states. So to get around this, there are several tricks you employ. You either choose Coulomb gauge, so you only retain the physical degrees of freedom, or you use for the indefinite metric space. But however, in this problem does not arise. Why? Because the eta mu is a space-like vector. So when you're writing in this a dot eta, if you see over here, this is a space-like vector, so you're only taking the particle that you are creating that is actually a cloud full of space-like photons. So let me rush through this thing. So if I want to write an effective operator for these objects, I did not write the fermions in here, but you can see that you have a psi bar psi, which I did not write here. So the psi bar, if you dress the psi with e to the power minus iq phi, the psi bar will get dressed by e to the power iq the negative of that, so you have plus iq phi. Now the difference happens to be noticed that if these two particles, remember this flux, the Wilson line operators I'm writing, if eta and eta prime are identical, then what happens, this thing actually exactly cancels. But if you have a situation, it's sort of like forming a domain inside a magnet, right? You can have one whole magnet which has identically oriented, the north and south pole, but there might not be long-range coordination in the system, so it breaks down in some pieces. You have a domain pointing in one direction, you have domain pointing in another direction, another region. And these domains, as you remember, the order parameter in this case is given by this eta. I'm sorry, if there are questions at any time during my talk, please raise your hand and ask. So this is what is happening, that you have this Z naught coming, and this is the infrared dressing. I'm not writing that. The red thing that you have, remember, that straight line that you have that represents the fermions, and the photons that I've actually superposed them together. This thing actually fills up the whole thing. You have this cloud of this infrared photons that you actually have. And the rest of the thing is pretty straightforward calculation. Those of you who have done quantum mechanics must have done something like coherent states. So you just simply do a coherent state calculation. Very straightforward. It's a fun thing to do. You simply use BCH formula. So here's a quick rundown of this thing. So I will expand A, as I had mentioned. You have this standard covariant expansion, A mu, in terms of d tilde k is the standard Lorentz invariant phase space, which often we shortenly call LIPS. And if you plug this phi value into this thing, you will have this integral. And what you find, the phi looks almost same as the previous expansion, but if you carry out this integration along that line where I have carried out the flux Wilson line, you exactly get this mode expansion, which is of this form. But this chi are related to the A, but remember it gets multiplied by a factor of k dot E minus, okay, there's a typo error. It should not be E, it should be eta. So I forgot to check this. Now in the I epsilon going to 0, you might notice that this is sort of a scale invariant quantity. Why? If you rescale eta, then the top and the bottom actually gets scaled identically. I epsilon is just a way to push you away from the real line. But other than that, eta is a space-like. So even you have collection, you have basically a collection of all space-like vectors. So in a sense, this is sort of like a de Sitter space. Not exactly de Sitter, sort of like, because it has a puncture that's taken out. K is not equal to 0. So now all you require is just write down the normal order product and do the calculation. So I will just skip through this because these are not something very interesting. If somebody wants to torture themselves, if you're a masochist, please walk up to me and I will redo the calculation. So you apply the BCH formula and you carry it out. Now the fun thing is that chi, remember, satisfy the standard commutation relation. Chi dagger is equal to Kronecker delta, etc. And you have this extra factor in the denominator. So the important thing is, thanks to the BCH formula, what happens, what you had this cancellation, naively you'd think, okay, I will have something left. But there is a phase that pops up. And this phase is just sort of like the Pauli-Jordan function that one actually has, but except this extra modulation k dot E in the denominator. That's because of the line integral that we did. And this is uninteresting. So if you do it, then this delta, this phase we have, there's an equal to sign that got actually swapped when I was editing this to fit this long line. It used to be a long line, then I started, try to fit into this slide. The important minus sign got chopped off. So there's a minus sign when the delta bracket ends. So it's equal to q squared eta dot. Now this integral, this can be done. Mathematica is quite good at doing this. But this is a function with certain branch cuts. So you do not trust Mathematica. I myself, I don't know, some of you actually love Mathematica. I, for example, are quite wary of it. So there's 3 of us, remember there are 4 of us that actually co-authored, but 3 of us did the integration in 3 different ways. And we agreed, yes, you can trust Mathematica. So this is the integral that you do. And this can be done by hand. And you have a very nice closed expression. I am not giving it. What happens is the integration actually has a logarithmic divergence, which is like this dk over k, where k is the modulus of this d cube k vector that we have. And the rest of this thing using the Feynman Schwinger as well, because I think Schwinger's paper also has them. So Feynman-Schwinger technique, you find this integral can be done, and it has, this is a divergent, logarithmical divergent integral. So to render it this some sense into it, we put an ultraviolet cutoff and an infrared cutoff. Both of them are actually necessary. And you have this integral that actually depends on this product eta dot eta prime. Remember, for Landau-Yang theorem, you need eta and eta prime to be the same, and it's a space-like vector. So when you plot the whole amplitude, I will skip this. This is interesting how to actually get around that logarithm. It's just you have to resort to, because remember the q square fact, so you have to appeal to the charge normalization of QED that can be absorbed. Then you find that there is this phase factor which actually has this form. There's a finite number in the exponential and this factor which depends on eta and eta prime. And lo and behold, you plot, you just simply see what happens, you are in different domain. So when the particles are produced, the particle production in the quantum world, there is no reason a priori for you to think that I and Tibra will wear the same shirt, because we make our choices independently. In a spontaneously broken world, the possibility of having 2 different values for that wave Having the same is less than having them different. So what happens if you plot this whole thing, the exponential factor, all of it in front of the standard one, the inclusion of the Wilson line operator gives you this increment. There's a factor that is non-zero. The question is whether you recover the known result. The answer is yes, because remember, eta and eta prime are space-like vectors. So in the plus minus minus, not Ashok's metric, the opposite one, the one that is adopted by California people, we call it West Coast metric. So you find this exactly vanishes. So this is interesting because even after the Wilson line integral's been added, we recover Landau-Young's theorem. But the important thing is, if you have a hypothetical world when particles are created and Lorentz symmetry is violated, Z naught goes to 2 gamma will not be suppressed anymore. And once you actually have this situation, you might want to call into question a lot of other symmetries that you take them for granted. Things like charge conjugation violation, parity violation. Parity is already violated, we already know that, but that's not part of, that's an outer automorphism of the Poincare group. So things like this, can they be, you have to re-examine what you believe or thought you believed. So that's basically what I ask you to do. And with this, I conclude. Thank you.
Questions?
Yes, Vishnu.
What I'm asking is actually not exactly related to your derivation or conclusion, but it's a curiosity on a related topic that is driving me off late.
That's why we are theoretical physicists.
The question is, I'm not 100% sure of the answer, that's why you may have thought about it. When in a Landau-Young context, the massive vector boson is off-shell, even then is its effective coupling with a pair of photons necessarily zero or not? The sub Z to gamma gamma, suppose it's an off-shell Z.
I will tell you something, which is while I was trying to do this calculation, nowhere I used the factor that Z has to be on shell.
Precisely, that's what is driving me. So is it always forbidden by Landau-Young theorem for an off-shell vector boson to couple to a pair
If you look at the theorem, the way actually the modern proofs go by, there is no restriction on that. So it can be, it should be valid also off-shell if you follow those derivations.
Yes, because off-shell Z is also a massive particle kinematically.
Exactly.
Excepting when it has q squared equal to 0, which is again a zero.
I mean, for the space like that, I understand.
Yeah, but it's a zero, what is called zero measure of region in the phase space. So probably it doesn't again contribute 0 to the effective coupling.
I think you have a point because it's a Lebesgue measure is 0 because it's only 1 point.
Yep.
Right. Okay.
Zero measure set. So,
well, I mean, the whole thing was just like an academic curiosity when we actually started looking at it. And this thing popped up. So we are now, in a sense, I know that the Landau-Young theorem actually is not valid for non-abelian particles because the way you actually do the breakdown of the amplitudes, there's a color index, so when you do the symmetrization, anti-symmetrization...
So when you mean, when it's a pair of gluons, it's suspect?
Not here. Here is not the case.
Yeah. Anyway, so this was my curiosity.
Thank you. I will think about it. As I told you, we are also looking at the positronium system because there's a good experimental test because it's cleaner.
Yes.
Okay. Thank you.
Okay.
So maybe another quick question if we have any.
If there's no question, I would like to actually add a little anecdote.
Please.
Just to keep people not falling asleep, which is when I was in 1988, when I was just a second year student, that's the first talk I gave in my life. That was also in a Bose symposium as a second-year student. And now I'm a 55-year-old person, again giving a talk at Bose. There's one, if I have not managed to, my only other connection with Bose happens to be Bose quit Dhaka University after 24 years of service. So did I. Thank you.
All right. So I would like to welcome our next speaker, who is Professor Parvez Khutboy. And he's going to speak about instantons and the quantum tunneling of a composite system confined within a double potential well.
This is this one is laser. Yes. Okay. Okay. I think I'm the last speaker, not just for the day, but for the.
Actually, there's one after.
Oh, there is one
Yeah.
after. Okay. Nevertheless, I will say that this has been an excellent conference. It's particularly valuable for those of us in South Asia who are unable to cross borders and can only do so when provided an opportunity by the team over here, Kamrul in particular. And so thank you very much for that. I'm going to be talking about a problem that I started some 3 months ago and have become quite engaged with. And it's to do with an old problem, and that's, of course, how you deal with strongly interacting systems. But first, let me define to you what an instanton is. It's not a particle. It's the solution of the equations of motion in some quantum mechanical or QFT system, quantum field theory system. It is in imaginary time for reasons that I will tell you now, and it cannot be just any solution, but it must have a finite non-zero action. And because it has a finite non-zero action, that means it's confined to a small interval of time and can therefore be thought of as a particle. But I'll be talking about this in detail. Whatever I've learned has been from these review articles. I think the first one is perhaps the clearest. It's old, but it has a lot of material in it. It's actually a prelude to the quantization of QCD, semi-classical, a semi-classical treatment of QCD. And there are now lots of good books, in particular this one by Schiffman, Advanced Topics in Quantum Field Theory. My interest in this problem was actually because of this paper that I saw a long time ago. Can our universe suddenly collapse? Collapse without warning. And this is an old paper by Sidney Coleman, who was then at Harvard, and you can see that this paper is written in 1977. It's to do with, now this is the paper that really got me interested in instantons. The reason is that instantons are a very important tool by which to understand tunneling. When Coleman said, can the world collapse? Here's what he had in mind. This morning we talked about the Higgs potential. Now the Higgs potential pervades all of space. So when the Big Bang happened, the universe had a certain Higgs potential to it. And maybe that was the genuine minimum into which the universe settled. But maybe it is not. So you see, the Higgs field is everywhere. The Higgs field, although it is electrically neutral, it has a charge under the weak force, and therefore the vacuum also has a weak charge. And you can go from a state of higher potential, higher energy to a lower energy. Now this is something that happens through an instanton. And it has to happen all over space and pretty much at the same time. But these instantons, as I discovered on reading this literature, are really quite important in other places too. So they are used for understanding chemical reactions, for even modeling neurons. And so that's what got me intrigued in the problem. So now here is the outline of my talk. I'll give you a brief outline of what instantons are, and this will be in the context of the double well potential in quantum mechanics. Now all this grows out of the Feynman path integral. The Feynman path integral is the way of doing quantum mechanics invented by Feynman back in the 1950s. And it's really now how we do quantum field theory. One doesn't usually study it in elementary quantum mechanics courses, but these days you could, I suppose. Now, how instantons then give rise to tunneling and how you can use them to compute tunneling rates and various physical observables, I'll talk a bit about that. And the hardest part in dealing with instantons is what is called the zero mode and the functional determinant which is associated with that. After that, I'll come to my own effort to extend this and double the double well, or maybe quadruple it, or maybe even further. I mean, I don't think that there is a limit to which you can go. But of course, it has to be useful for something. And I will try and persuade you that two double wells coupled together give you an interesting physical system and give you a way of attacking a problem that so far nobody has successfully solved. I mean, there are ugly ways of doing it, like coupled channels in nuclear physics, but those are heavily computational. They give you no insight. On the other hand, this could give you a fresh way of looking at problems such as those. Although most of the mathematics will be pretty mundane, but in this system, it turns out that there's not one kind of instanton, but three different kinds. And the ways in which you can combine them actually are so complex that you start to need graph theory. And so graph theory is one of the things that I'm presently learning. I never thought I would, because it's abstruse. It seems to be abstruse mathematics, but it's actually very useful. Okay, so in undergraduate quantum mechanics, everyone learns about tunneling. You learn about how to match the wave function and its derivative, and in this way get the transmission probability from one side of the barrier to the other. And in the WKB approximation, you learn that it's this exponential, well, anyway, you can see it on the slide over there. So you have classical turning points where the energy and the energy of the particle is equal to the energy of the barrier. And so you do an integral from A to B, and you get an answer, and that answer is actually correct. I mean, you can check it numerically. Now, this is an answer that you could not get by using perturbation theory. You can sort of see that because it's got an h bar at the bottom, and if you let h bar go to 0, then that becomes e to the minus infinity, which is 0. So classically, you would have no tunneling. Now, that's what you know. Okay, so now very briefly about the Feynman path integral. It says that if you want to go from point A to point B, whether that is in real space or in configuration space or whatever space, well, you take all possible paths that connect A to B. And those paths can be straightish, or they can be of any shape. They can even be jagged and non-differentiable, but then that would not weight the integral much, and in fact you could neglect non-differentiable paths. The slight mathematical complications are that you get infinities in the normalization, in the integration measure, but we know how to handle that. All that is in the book by Feynman. So that's the usual way of doing things. But you see, there's a problem because there's the evolution operator is e to the I ht divided by Planck's constant h bar. But that oscillates wildly. And the bigger h is or t is, the more it oscillates. And so in quantum field theory, one likes to go to Euclidean space. So you use imaginary time. You let t go to I times tau, where tau is real. And so then you get something that's damped. Okay, now let me say why the double well is so interesting. Everyone does it in single particle quantum mechanics, of course. You use it for various now different systems. It's also the way by which you introduce spontaneous symmetry breaking when teaching quantum field theory. And this is really the introduction to non-perturbative physics. So why do I say it's fundamentally non-perturbative? Well, one reason I gave you, but here, if you look at this double well, you'll see that the very lowest level would be that which is harmonic oscillator-like. I mean, it's not a harmonic oscillator because it bends over, but if you're close to the bottom of the left well, then it's almost quadratic over there, and so almost simple harmonic. Well, now there's the left well and the right well. There's a symmetry of x goes to minus x, which means that your wave functions will be either symmetric or antisymmetric. Now, if you try to compute the difference in the energies of the symmetric and the antisymmetric one, you can't do it using perturbation theory, because this is fundamentally a non-perturbative problem. In perturbative physics, there's no way for the particle to cross over. Okay, now I'll come to instantons, give you a first quick look at it. So here's, imagine there's a particle, the little red dot is a particle. If you don't do anything to it, it will sit at the bottom of the left well, and it'll just keep sitting there and do nothing. If h bar is 0, it'll do nothing. Okay. Now, when I make t go to I tau, well, then I change the sign of the potential, effectively. And so here is the inverted potential. Now, what I've simply done is I've flipped it around, and so a particle which is, a ball which is sitting at minus a will start rolling down, and it will reach the other peak at plus a. Newton's law which you've always known as x double dot is equal to minus dv by dx, now takes the form x double dot is equal to plus dv by dx. And the conservation of energy, instead of it being kinetic energy plus potential energy equals a constant, it becomes minus kinetic energy plus potential energy equals 0. So big deal, you'll say, what do you gain by this? Well, now you can have different kinds of solutions of the classical equations of motion, and this is going to bring me to instantons. There's one solution where you put the ball at the top of the hill and it does nothing, it just keeps sitting over there. But then there's another type which will start rolling and go to the other end, to the other peak. And if you just take the equations of motion, you don't have to have a particular form for v of x, but if you have a simple form, well, you can work it out analytically. The solution of the equation of motion looks like what you have before you. So a long time back in the past, you are at minus a, and at a long time into the future, you are at plus a. So in effect, you are in two different vacua. This is actually a topological object. It goes from one vacuum to another. Now, if you have an explicit potential which is simple, which is like this, then you can just solve the differential equation, and it's just a tan, the hyperbolic tan of tau, omega tau over 2. Now, if you look at the equations of motion, they're time reversal invariant, so there's also something called the anti-instanton. And this anti-instanton will take you from the peak at plus a back to the peak at minus a. And so you can have bounces from left to right, right to left, left to right, and this can go on indefinitely. And each one of those bounces will give a contribution to the action. So the equations of motion have as solutions, and in this very trivial example, zero instantons means that there's nothing moving. Then one instanton in which the ball goes from here to there. Two instantons mean back to where it was. Three means again go there, etc. And now, because of time translational invariance of the equations of motion, you don't know when a particular instanton is going to start and when it's going to arrive at the other peak. So there's randomness over here, and so you have to integrate over all possibilities. Okay, so here's an example of just three instantons and three anti-instantons, and you can see that they go up, down, up, down, up, down many, many times. Each one of them carries a certain classical action with them. Now, those classical actions have to be summed over, but you can do that only if the instantons are suitably separated from each other, which means that you're thinking of the instantons as kind of dilute atoms in a gas, in a one-dimensional gas. And so this is what you call a dilute instanton gas. Nobody really has figured out how to deal with instantons which overlap substantially with each other. You can do some sort of corrections, but they're not very convincing. Anyhow, so here you now get an expression for the amplitude, the Feynman amplitude to go from one well, from the top of one well to the top of the other well. And you can, once you sum them up, you get nice, very nice analytic expressions. They are either Shine or they are Koch. I'll explain where K comes, the K that's mentioned below, that's where all the hard calculation is. Okay, so now I've told you the classical part, now let me tell you about the quantum part. So suppose that there is some classical path which has been determined and is determined by solving the equations of motion. Now, Feynman says that is not just the classical path, but all possible fluctuations around the classical path have to be taken to compute the amplitude. And so the most general path will be this, where the fluctuations vanish at the edge points, at the end points. And so therefore, take the action, expand it in a functional Taylor series. So a functional Taylor series, just like, the sort of series that you have for expanding functions, it's a little, just 10% more complicated. And here's what you get. But of course, because we've identified the equations of motion from the principle of least action, we can just throw away the linear term, the linear in xi, and we're left with the fluctuation term. So that's as far as we can go with quadratic fluctuations. Oh, I am very slow. Well, the problem is there is a zero mode in the problem, and the zero mode makes this a little difficult, but basically what you have is you need to diagonalize an operator. That operator has an infinite number of eigenvalues. If one of those eigenvalues happens to be zero, then you're dividing by zero, which means that you get nonsense. So if you get nonsense, that means you can't proceed any further. You have to deal with that. Okay, now since I'm late, I am going to tell you about the model that I think is useful and which I'm working on and which hopefully will be completed in a couple of weeks. So imagine that you have not a point, but an extended object. So for example, a diatomic molecule which is in a potential, in a double well potential like this. What's the amplitude that it will go across? Now you see, if you think about all the tunneling problems that you've seen in your life, I bet you haven't seen one with a composite object. When George Gamow did his calculation of the alpha particle tunneling across through a nucleus, he said, oh, take it to be a point. There's a potential and a point in which that alpha particle makes its way out. Okay, but you know the alpha particle is not a point. You know the diatomic molecule is not. And so here is this is an obvious sort of model. Suppose I take these two atoms separated by a distance L with a spring in between them. Then I can write down the potential in terms of their coordinates. If I write it down in terms of the relative and center of mass coordinates, and now if I minimize the potential, and so this is a quadratic form and can be minimized, then I get a very simple but very, but a potential which has deep consequences in it, built in it. So these alpha, beta, gamma are coefficients which depend upon the original parameters, the masses, the separation between the wells, the distance, capital L, and so forth. Well, then comes treatment of this. So you can make a scale transformation, put all the wells at the same level, and now instead of 2 peaks, I have 4 peaks. And now the ball can be on any one of the 4 peaks, A, B, C, D. It can go from one to the other. And so this is a much, much richer problem than the one that has been considered for 30 years or so. And I'm surprised that nobody did this earlier. You can not only put in different degrees of freedom, but how these different degrees of freedom can surmount potential barriers and get to the other side. So in the case over here, let me go back. You see, I labeled the diatomic molecule with two different kinds of atoms. One was red, one was green. But look, it can go to the other side, and in doing so, it can flip. So it's not actually just one flip that we're looking at. That is, it's not just going from left to right, but also the molecule flipping around. And now you can imagine that I can have other degrees of freedom that will flip, that will tunnel through. And so there's a lot over here. But then, can you solve it? I mean, what's the good of writing down a model that you can't solve? Yes, the answer is you can solve it because you can identify, at least in this problem, certain small parameters. What small? Well, one thing you could do is you could shrink the molecule down to a point or nearly a point, then look at the corrections as it's not a point. Secondly, you could say, this molecule is so stiff, it's not bound by a rigid rod, but the spring is stiff, but not too stiff. Okay, so all that gives you small parameters. So you can imagine, I can imagine that this will be useful in other areas of physics. What do you have to do? You have to solve the classical equations of motion. Can you solve them? At first, I thought it would be impossible, but then it turns out you can do it because there's a kind of topological protection that's being given to you by the fact that you go from one vacuum to the other, and you always have to go from one vacuum to the other, and that's why perturbation theory on a non-perturbative problem is possible. You, again, in a broader sense, energy is conserved over here. You have to define the energy differently. There are quantum fluctuations. Which? Oh, yeah. Which one over here? That's right. Oh, yes. Oh, yes. That certainly does not put p equal to plus or minus 1. Yeah. I should have written alpha 1, alpha 2, alpha 3, alpha 4, but yes, thank you. Okay. So then, I've run out of time. Basically, what you do is you find closed expressions for the propagators. A little complicated because the equations are a little, it's not. You can do it. It takes a while. You can then do the functional integration, avoiding the zero mode. The zero mode you handle just like the good and the great told you before. You integrate over time. And then you write down the Feynman rules for the system. You do normal quantum field theory, actually. What you learn from quantum field theory, you apply it to a quantum mechanical problem. And so finally, I will say that we have an interesting system which has now an arbitrarily large number of horizontal, vertical, and diagonal instantons. Now, how to sum over these sequences of instantons, this is the last thing that I'm working on. I think it'll be done very soon. But graph theory, these computer science books, they actually make things quite easy. So, I mean, these mathematicians, they write too difficult. Their papers are too difficult. But the computer science people, they'll tell you how to weight the nodes. And so I've almost done this. So that then, this is my second last slide. With very little effort, I am able to compute this Feynman amplitude in explicit form. It stands before you for something that has finite width. So this molecule has length L. So this connected by a rigid rod, you could say. which means I take the spring constant going to infinity, and with this amplitude that you have before you, you have the tunneling probability, the propagator from going from here to there. If you want to look at the splitting between the symmetric and anti-symmetric states, it's, I haven't written the expressions here, but they come easily. And of course, there's no spin flip over here because I've taken omega to infinity. But that is where this piece of research is going. You can hopefully go to more double wells or triple wells or whatever. And what these wells will represent is up to the imagination of the user. But here is a concrete use in tunneling, which otherwise seems to have escaped people's attention, or when they have tried to solve the problem of composite tunneling, it's extremely ugly because they try to diagonalize the Schrodinger equation in a bunch of basis states, and then they come up with these big matrices which computers can solve. You get no insight into that. Okay, so I think I'm done and happy to hear questions, have questions from you.
Please.
Yeah, so, double wells are used in a lot of areas, right? I mean, basically any phase transition you're thinking about. When I think of in condensed matter, that's basically what we will be talking about. So how do instantons come into this picture?
Okay, so I'll tell you how instantons come into account in phase transitions in a bigger system. And in fact, Coleman did that calculation back in 1977. With a phase transition, let's take bubbling. So you superheat a liquid and there's a little bubble that's formed. Now that bubble will either expand or it'll contract. Most of the time it'll contract, come back. But once it crosses a certain critical size, then it'll expand throughout the liquid and blow the liquid up. Mm-hmm. And that's a phase transition. Mm-hmm. Okay, so that's actually the calculation he did for the universe. Mm-hmm. Once
right, so once it does, then it...
Yeah, and so what you would have is a wave coming towards you at the speed of light. Mm-hmm. But in terms of phase transitions, in things like actual liquids,
there'll be dissipation of other kind, yeah.
Yeah, you have to look at bubble formation, and right. There is a potential that has to be surmounted.
Yeah.
Okay, I think Vishal, you have a question for that? Oh, yeah. Can you speak into the mic?
That's the other mic you're speaking into, not yours.
Use Nazia's mic.
That could be good enough. Oh, now it is working. Yeah. So, a very interesting talk. I just wanted to make sure that I understood it correctly. Are you saying that extended object that we have here, the 2 points separated by length L, that solves the classical equation of motion?
What is the
extended object, the 2 points, the 2 points that you have over there, yeah, separated by L?
Yeah. Okay, so there's no equation of motion for the relative motion because I fixed the
distance,
the rod. But that's only to show you this particular case. In general, yes, there'll be a spring, mm-hmm, or something, something springy, whatever. It doesn't have to be completely harmonic. And that, of course, is what gives you the restoring force. So it'll oscillate. It could also go through each other, which means that if you put the molecule in one spin state, so it's pointing one way, it has a direction to it, red to blue, let's say. On the other side, it could be blue to red.
Well, my question is, this composite object that you have, either are connected by a spring or in this particular approximation, would that solve the classical equation motion in Euclidean time? Is it really an instant-on solution to begin with?
Okay. So, in the simple model that I have over here, yes, you can.
Okay.
You have to make a series of transformations first, but once you get to the bottom of the potential well, once you get to the potential minimum, then you have these four peaks come on all sides. And then it is perturbatively solvable.
Right.
Instantons plus perturbations on those instantons.
Got that. Okay. Thank you. Got that.
So there you have a question.
Is there
Yep.
Yeah. I was wondering, I mean, you just basically have to have two states, right? Which actually has,
I mean,
same for the domain wall as well. Sorry.
no, go on, I'll talk.
No.
I think we have time for two questions. Yeah, it's.
Since you have two particles, I mean, this is what basically Dr. Akbar was asking, but you can put more and more particles. Can you think of like a wave that's tunneling through the barrier?
Well, look, I think it's not particles, it's degrees of freedom that are coupled to each other. So yes, of course, you can put more particles, yes. You could put potential wells between them so they could flip their position. So in principle, you can take as many double wells as you want to.
What I actually had in mind is like if you have like a condensate, like a BEC condensate, that
If I have a what?
a BEC condensate, B condensate, Bose-Einstein condensate, because that's you think of a lump, right? And you could actually create like a double well situation and see what's, because there can be some experimental realization, I presume.
Well, look, it's particle mechanics. If you can reduce it to the level of kinetic energy plus potential energy and identify what they are, then yes, you will have the soliton, the instanton solution, and then whatever you want to do with that.
Sorry. Oh, is it? Can you hear me? Yeah. Okay. I want to bring a different topic mostly to the audience, and I want to bring something about Parvez good boy. Probably he'll get red on the face, but it doesn't matter. So something that maybe you don't know. In 2005, there was a huge earthquake in Pakistan. Many of you will remember. More than 10,000 people were killed. So the point was, even people like me who were at the time very far away and only watching the news, I was getting furious in watching the news because I was saying, I mean, there were so many people dying, and the government of Pakistan was not doing much. The Americans who were in Afghanistan were doing zero. And even so horrible was the whole thing that one of the American journalists shouted, who was I don't know if he was Pakistani or Indian, because sorry, but he shouted on the TV, where are the helicopters? I don't know if any of you remember that, but he shouted that and he was cut. Right there when he shouted, he was cut, and for a couple of weeks we didn't see him anymore. Well, what I want to bring is that don't ask me how I got the news, but I got it. So then I knew that Parves, obviously must have asked some of his friends, and they got whatever it was. He knows the details from me. Probably vans or trucks, I don't know. He collected all sorts of things that were necessary for the people in the earthquake zone, and he drove to the earthquake zone with all of that, and they stayed in that region of Pakistan for 6 months, okay, helping of these people. So what I wanted to tell you was that Parvez is not just a very good physicist, he's an excellent human being. So Parvez, thanks for being.
What can I say? Thank you very much. But I think that students here, teachers here, if there was a cyclone in the Bay of Bengal, wouldn't they all be helping? So in that sense, we all have to help whoever is in distress. But thank you for remembering that. I had forgotten.
So it's late, and we have before the tea break. Oh, okay. Is there one more question, or?
Kevin, you had a question?
I did have a question. Thank you for noticing. I was going to ask you later, but I'll go ahead and ask it now if there's time. So when you have this inverted potential with the four peaks, you're looking at these instanton trajectories that are going from peak to peak, right? And some of these trajectories are given basically by symmetry. These are the ones that you drew in your graph. But I believe, given the fact that this is a two-dimensional chaotic potential, that there's going to be a wealth of a lot more trajectories that you might have to sum over. So that's just maybe something, maybe you've considered this already, but just something that struck me that might become an issue.
No, it's not chaotic. It's perfectly deterministic. I mean, the amplitude, you'll just get one formula for the amplitude, but you'll have to sum over all possible distances between instantons. I mean, the time differences between instantons. The reason it's complicated is because one instanton can start here, go to the other peak, then return by a different way, and you have to sum over all of them.
Right.
But there's no chaos over here.
Well, it's a two-dimensional potential, so unless it's separable, it will have chaos. Chaos doesn't mean stochasticity or randomness. It's deterministic chaos. It just means there'll be a wealth of trajectories.
Yes, every possible trajectory that there can be must be summed over.
Right.
None should be left over. And so where's the randomness there? Yeah.
There isn't any randomness.
So randomness in the sense that, okay, one instanton leaves its home. You don't know when it'll leave its home. It's the peak. And you know it's going to take a very long time to get to the other peak. The reason it's called an instanton, and this I should have explained, is that when it comes down into the valley, it zips through the valley in almost no time. Mm-hmm. So in fact, order of 1 over omega, and that goes to 0 if omega is large. But there's no randomness in the sense that once you've integrated over all possibilities, nothing's left over.
Right. It's just that the structure of all the allowed trajectories, it isn't random, but it is very complicated. It might be more complicated than you might think.
Okay.
All I'll send you an email.
Okay, thanks.
Okay.
Thank you
let's
for a
thank
nice
the
talk.
speaker again. So we have two quick talks now, and the first one is going to be by Muhammad Faisal Kabir, and it'll be first epitaxial synthesis and characterization of MNSP, INSP, I don't know what they are, hybrid structures of gallium arsenide 111B for spin FET applications.
Good afternoon. Thank you so much. I am MD Faisal Kabir, and now I am doing PhD at Japan Advanced Institute of Science and Technology, as well as I am the scientific officer in Bangladesh Atomic Energy Commission. Today, the title of my work is First Epitaxial Synthesis and Characterization of Manganese Antimonide, Indium Antimonide Hybrid Structure on Gallium Arsenide 1B for spin FET applications. And actually, the metal-based semiconductor device, metal-based spintronics device like GMR, TMR, and MRM already commercialized. So our group, we already focused on the semiconductor-based spintronics device. So here, the here the ferromagnetic materials actually give the spin, and the hybrid structure will be made by conventional semiconductor, which is actually the contributor of the charge, and the total combination is called the spin electronics. Here there are many ways to control the spin as well as the charge. First of all, the magnetic element doping or nuclear spin. But our target is used to the spin orbit coupling mechanism, especially the channel materials where the spin orbit coupling should be occurred here. So our final target is make a spin transistor like this. Here the ferromagnetic source and ferromagnetic drain, as well as the semiconductor channel where spin orbit coupling must be embedded, and here the gate materials. And the final output will become automatically on and automatically off state, which is helpful to the save the device power consumption. So this is the main target. And for this reason, we already did some works, actually the manganese arsenide and indium arsenide based, and we already published some works here. But the problem was that our spin signal was very weak, especially in these materials. So here we want to change the materials and to improve the spin signal quality. So we choose the high Curie temperature materials like manganese antimonide and small band gap material like indium antimonide. So we want to make a hybrid structure, as well as we have no experience previously. So we individually growth these materials by molecular beam epitaxy, and then we make the hybrid structure. So first of all, why we choose the manganese based ferromagnetic materials? Here the manganese antimonide, the main reason of that, their Curie temperature is higher than the manganese arsenide. So we think that the higher Curie temperature can help to improve as a ferromagnetic source or ferromagnetic drain. As well as the manganese antimonide is the hexagonal and the 6-fold symmetry, which is very good stacking on the gallium arsenide, which has the 3-fold symmetry. And the indium antimonide has a narrower band gap, especially if we compare with the indium arsenide. Is the band gap and the electron, the effective mass also lower than the indium arsenide. So we also choose the indium antimonide for improving the signal qualities. Then first we try different temperature growth, as well as fixing the beam equivalent pressure of the different cell. Here we initially we found that this not the single crystal, that polycrystalline in some temperature, but in some other temperature we find out this nearly single crystalline. Then we check the EDS and ACM. Here we find out that there are some good crystallinity and there's good coverings 400 and 500 degrees Celsius, but others the result is not so good. Then we picked up the suitable temperature 400 degrees Celsius. Then we also checked our growth is epitaxial or not. So we applied electron backscatter diffraction, and here we find out that actually in the gallium arsenide and manganese antimonide, the direction on and 0 on is vertical. So we confirm that our synthesis is the epitaxial synthesis. Then we focus the magnetic properties, and here we found the good magnetic properties for 400 degrees Celsius. Here the higher saturation magnetization as well as the very lower the coercivity. So we choose this condition, and then we forwarded and tuning little bit about the manganese and antimonide beam equivalent pressure by fixing the growth temperature 400 degrees Celsius. Here in the XIII, we also confirmed our manganese antimonide 0002 as well as 0004, and antimonide and manganese ratio 3 BEP showed very strong, high magnetic saturation as well as the very lower coercivity. Then we also check the surface coverance, and we find out that the good coverance at that condition. And with AFM, it's little bit rough, but AFM also good agreement with the ACM and other results. Here the RMS velocity, RMS value was near 15 nanometer. And as well as then we focus on the indium antimonide. And here the indium antimonide case, we also follow the similar rules, and we find out that the good condition is the 400 degrees Celsius from the XRD. We confirm the indium antimonide on as a single phase, and as well as 333 indium antimonide in for all the cases. But for the ACM observation, we find out that the 400 degrees Celsius, the surface looks usual compared to other two temperature growth. Then we also use the electrical property. Here 400 degrees Celsius growth especially showed the higher mobility compared to other growths, and we also check the temperature dependent mobility as well as the resistance, which is very traditional, as well as the good semiconductor materials. Then we focus on the heterostructure like this condition, and the figure A, actually this is the R heat observation, and where we confirm our thermal cleaning as well as our structure direction is like figure B. We want to growth like this way, indium antimonide, then stacking with manganese antimonide. And we also did it successfully, and in the XRD we confirmed indium antimonide 1 as well as manganese antimonide 002 as well as 004, and we also use the omega theta scanning. Here we confirm that the epitaxial relationships also confirm using this condition, as well as the manganese antimonide layer, indium antimonide layer, also gallium arsenide layer. Then we also check the EDS and ACM. It is the indium antimonide layer. We also confirm indium and antimonide, as well as the upper layer. We also confirm the manganese and antimonide by ACM and EDS. Here we also check the AFM, but in the AFM we find out that the upper layer, that means manganese antimonide layer, showed very large roughness, especially 28, at double of the single lower layer. So we think that there are some deformation or dislocation density also very high in this case. So we are also using now some techniques to solving these issues, as well as we also measure the squid measurement and the saturation magnetization of that heterostructure. Here we also find out that similar magnetic properties like the single manganese antimonide layer. So we confirm that this layer has a good manganese good magnetic property as well as the electric property, which is very essential for our devices. So then we also focus on our device fabrication, and actually we would like to first of all we would like to make spin bulb device, especially local and non-local device. Then we want to move our final target spin field effect transistor, and we want to we hope that it will be improve the signal of the previous materials. So that's the summary. We completely synthesis manganese antimonide single layer as well as indium antimonide single layer. Also we completely growth the manganese antimonide and indium antimonide heterostructural layer. Finally, we also evaluated all the electrical, morphological and magnetic properties, and we have a plan to switch device fabrication as soon as possible. So thank you so much for your kind attention.
We have time for questions.
You claim that this is the first ever work done. Is that so?
Where? Oh, yes, sir. It's
How?
first. If it axial growth, that means heterostexture the first.
No other work was done
No, no
before.
other individual layer has, but no heterostexture history.
This
is the
work
first.
has been done in which lab in Japan?
Me?
Yeah.
Oh, it is Japan. Japan. There's maybe your daughter also at that university, ZAIST.
Which university in Japan you are carrying out this work?
ZAIST, Japan Advanced Institute of Science and Technology.
Uh-huh.
Maybe your daughter also at that university.
Yeah, here.
Yes,
Thank you.
Thanks.
Okay, any more questions? If not, let's thank the speaker again. Thank you so much. So our last speaker before the tea break is Syed Fariduddin Farhad, and he is going to speak about development of a portable LED-based light source with selectable wavelengths, intensities, and illumination periods for photophysical and photochemical studies.
Good afternoon, everyone. So, I am actually Mohammad Saidul Islam, Scientific Officer from Industrial Physics Division, BCSR, Dhaka Laboratories, BCSR. On behalf of Dr. Syed Fariduddin Farhad, I am going to present this talk, development of a portable LED-based light source with selectable wavelengths, intensities, and illumination periods for photophysical and photochemical studies. So, I'll be very brief with my presentations as we are at the end. So why do you need a light source? You know, in solar cell, if we want to find the efficiency and related parameters of a cell, we need to use a light source. You know, basically, solar cell is basically a stacked layer of films. So if we want to find the qualities of different layers of that films, we need to use a light source of different wavelengths. Contemporary researchers are working on water splitting device where these types of device use sunlight to split water and produce hydrogen and oxygen, where hydrogen can be used as a fuel. So to do these types of research, we also need a light source. If we want to see on a different perspective, you know, dyes that are released from industry, leather industry or textile industry, that are very harmful for our environment. So we could degrade these dyes with photocatalysts. So for these types of research as well, we need a light source. So are there any light source available? You know, there are many types of light source like a xenon arc lamp and so on, but we got some problems with those light source. We find that these are mostly expensive and these are not portable. You put them on one part of your lab and do everything there. They have limited functions and they are limited in their applications. One type of light source is only used for one type of experiment. So to resolve these issues, we worked on developing a light source. So this is what we have developed in our lab. With these components, we build this light source. Though the prominent features are, we have alterable LEDs. We have alterable LEDs where we can change the LEDs to get a wavelength. A control unit here, I'm going to explain it later. We also have a neutral density filter to regulate the intensity. So to look a bit more to the features, we have variable wavelengths from 370 nanometer to 845 nanometer. So we are covering from UV to NIR range. We can add some more wavelength to this. You can see here there are visible wavelength here. We also have a white LED, so we have which has a broad spectrum. So we have different LEDs or different wavelengths. To talk about intensity, we can change the intensity by controlling the current to the LEDs and also by changing the distance. As our light source is portable, we can put at any distance from the sample. So here is our portable light source. You can see we can put it from the side. We can illuminate from the side of the sample. We can put it over the sample. We could put it under the sample. So we can put it anywhere in special position. Then to talk about stability, you know, LEDs they get heated and the wavelength may get shifted, but we experimented that and for some times we kept those on and you can see the peak wavelength or intensity or full width half maximum, they do not get that much shifted from the original position. The stability is good. So we have used this light source in different experiments. I'm not going to go through much detail here as I do not have much time. So we have used it at photovoltaic characterization of a CDT or cadmium telluride solar cell. You can see with different intensity we found different current density. So from these types of data we can, with selectable or with respective wavelength, we can get the carrier transport, we can get an idea about the carrier transport in different layers. So we have also done light intensity modular impedance spectroscopy. You can see, so from those devices or from cadmium telluride solar cell, we have conducted this experiment as well. We have conducted the electrochemical impedance spectroscopy. So from these types of data, we can get an equivalent circuit, as well as to explain some more. You can see from the low frequency region data, we can find out how the interface of cadmium sulfide and cadmium telluride are behaving. So we can get a qualitative measurement of how the interface are from these types of data. So here's another experiment setup for determining photo response. We used this for a CZTS solar cell with different wavelengths of light. Now, blue LED of course have higher energy than green LED. So we have got more photovoltage for blue light than green light. We have also used a red light. You can see it has a higher photovoltage initially because it goes deeper and create electron hole pair, but they have to go on a long way to go to the contact, metal contact, so they get recombined. So the photovoltage ultimately gets decreased. So with these types of data, we can get an idea of what is happening inside the layers. We have developed zinc oxide nanorods in our lab. So what we have done here is, for example, we have two types of nanorods. The top figures are for one sample and the bottom figures are for one sample. So I'm going to explain the top samples, what is happening here. So our zinc oxide nanorod, we first measured the water contact angle, and then we illuminated the zinc oxide nanorods with a light of 410 nanometer that has an energy lower than the band gap energy of zinc oxide nanorod. So the contact angle doesn't get much changed. But when we expose the nanorods to 365 nanometer of light that has slightly higher energy than the band gap of zinc oxide nanorods, we get a huge change in the water contact angle. So we can verify that our zinc oxide nanorod has the desired band gap that we are looking for. We have also conducted the photocurrent of those zinc oxide nanorods. You can here see the same image, ACM images of those zinc oxide nanorods. So for two types of data, we got two types of current density. So this is a comparative study. We have also done photocatalytic activity of photoelectrode material. So at first I have shown a photoelectrochemical water splitting device that has photoelectrode like copper bismuth oxide or bismuth oxide. We have also done some photocatalytic activity or EIS measurement with those devices as well. So I can move on to the next slide. We have then copper bismuth oxide. We have conducted the phototransient response of copper bismuth oxide cathode. You can see we have measured the photocurrent. So from these types of data, you can get an idea whether the device you have synthesized is a P-type or N-type. If it is the photocurrent gets lower with light, you can say this is P-type, or it gets higher, we can say it's N-type. So we can do many things with this light source. To summarize, we can say that we can do the photophysics and photochemistry related work with this light source, and its unique features enhance the research scopes. So to acknowledge, I would like to thanks to the scientists from our division. We have also Mohammad Saidul Islam from another unit of BCSIR. So I'm also acknowledging BCSIR and Ministry of Science and Technology as well. So before wrapping up, I would like to inform you that we have applied for a process which already has been accepted, and we also have applied for a patent which is under verification now. So thank you.
Are there any questions? I have a question. What's the price of one of your devices?
So the components we have used, it took 5 to 6,000 taka. So to industrially build those lights, it may cost around 10 to 12,000 taka, considering all the costs.
Okay, thank you so much. Yeah. Any questions? If not, let's thank the speaker again. So I've been told there's another talk now by Ahmed Rakin Kamal, and he's going to talk about back to the origin of brain anti-brain inflation. Do you have a laptop? You can hook it up. Yeah. HDMI port? No, sir. Nafis. Nafis, that's it. Does anyone have a HDMI dongle for Mac? HDMI dongle আছে?
Can I send it by email or something?
Yeah. What email would that be? Yeah, sure. Now I have one of those and it's outside, so Tamid is just going to go and get it. So, so it doesn't. You don't reckon you don't have to. Tamid is getting the dongle, and you can use that. So I guess I missed the conference picture yesterday. Yeah, I went home. It was so far away. Pen drive, you do have a HDMI. Give it to me. No, I say HDMI. He just doesn't know. Kids these days. আমার HDMI নাই. You have 10 minutes.
Should I start? Hello, everyone. Thanks to the organizers for letting me speak at this conference. So I will talk about the paper we put out 2 months ago on brain anti-brain inflation with a collaboration with Michele Ciculli, Francesco Marino, myself, Fernando Quevedo, Gonzalo Vera, Mario Ramos Hamud. So I'll try to be very brief. So problems of standard Big Bang cosmology required an early period of accelerated expansion. So like in the very early universe, you had an rapid acceleration of space and time, rapid acceleration of space, which solves the problems of standard Big Bang cosmology. So in the current stage of cosmological storytelling, you can see that the universe is expanding, and it's something called the dark energy dominated era of our cosmological storytelling. So we need realistic scenarios where constraints from experiments are satisfied and we can complete our cosmological storytelling. So dealing with them usually signals a breakdown of our naive effective field theory analysis, and we need a quantum gravity treatment to solve this problem. And our favorite one is string theory today, and we'll give a framework where you can study gravity and quantum mechanics together in a consistent fashion. So inflation is usually described by a scalar field, which gives the rapid expansion of space in the early universe. And observationally favored scenarios there are two types of potential which are observationally preferred. These are of these two types. And in string theory, there was this famous example in the early 2000s, which is called the brane and an anti-brane inflation. So it was the first of its kind which provided us how inflation can happen naturally in a quantum gravity framework. So a brane is an object which is, for example, a D0 brane would be a particle or a zero-dimensional object. A D1 brane would be a string, a D2 brane a sheet, and so on. So, and an anti-brane is the same object with opposite charge. But it had a few problems. I won't get into the details since we are short on time. So it was very hard to solve all of these problems in a string theory analysis. But in our recent paper, we showed that all of these can be possible. And on top of that, we found a way to have a late time accelerating universe or a late time accelerating cosmology or a de Sitter cosmology using perturbative corrections from string theory. So I'll quickly describe what inflation is in this scenario. So inflation can be described by a scalar field. So in this setup, where does this scalar field come from? It's the separation between the brane and an anti-brane. The potential is of this experimentally favored form. So that is one of our motivations to look into this potential. So in string theory, there are these two kinds of corrections, which are alpha prime and GS corrections. Alpha prime corrections are like those of us who know about the Einstein-Hilbert term. These are like higher derivative corrections to the Einstein-Hilbert term. And GS are these loop corrections or different loops you can form in using strings. So using these corrections, we can construct supersymmetric ingredients, and you can construct potentials. So why are we interested in scalar potentials in general? Because scalar potentials in general usually tell us that at the minima, it can be shown that it gives us the cosmological constant. And cosmological constant is something that can be understood. Cosmological constant can tell us about the late time accelerating universe. If it's positive, then you have a de Sitter expansion. And we have found a family of solutions where we have anti-de Sitter solutions, de Sitter, and Minkowski. So as I said before, I will not go again into too much details. These were the problems of brane-anti-brane inflation, and we tried to solve this problem using perturbative corrections, as I said. And the trick we used is actually using the whole, in string theory compactifications, as we know, it's a 10-dimensional theory. You have the 4 dimensions of space-time and 6 extra dimensions. And we used a combination. If you're using perturbative corrections, we used a combination of the volume mode and the inflaton. So a perturbative correction will stabilize sigma in this setup, and you can get away without the eta problem. I know this is too short, but I'm happy to elaborate if you have any questions. And the potential, as we see again in equation 7, it's of the experimentally favored form, and we studied these things in a complete string theory setup, I think for the first time. And so as we are studying things in string theory or a quantum gravity theory, there are constraints from experiments, there are constraints from the UV theory, which in this case is string theory. So there are these constraints in the setup which we imposed, and some of them I have not written. So these are the constraints from string theory analysis, and there are constraints coming from experiments. And combining them, we tried to plot out the parameter space, and the parameter space has non-zero contributions. In a sense, you can see we have a large portion of parameter space where brane-anti-brane inflation can happen. So in conclusion, we solve the eta problem of brane-anti-brane inflation. So this method of solving the eta problem using perturbative corrections in string theory, I'm happy to elaborate more. It seems more general. So there are people at Brack University, we are trying to understand other inflationary mechanisms or other inflationary methods which can be mechanisms which can be applied to see if brain anti-brain inflation or more exotic inflationary mechanisms the eta problem in those mechanisms can be solved. So again, as I said, we obtained 4D-dimensional de Sitter solution. A de Sitter is the one that says our universe is expanding. And we connected, usually in inflationary model building, usually do not connect the early time and late time physics. We connected the early time and late time physics along with satisfying the effective field theory constraints which are coming from string theory, plus experimental constraints. But our storytelling is not complete yet, because we are telling the story of the early universe and the late time universe. There is something else missing. That is, you can have, for example, dark matter, as we were seeing throughout the conference. We have not addressed the issue of dark matter in this model, and we have not tried to build standard model in this setup. Then it would be interesting to see if we can do that. So with this, I conclude. Thanks.
Thank you, Rakin. Are there any questions? If not, I actually, oh, please, sir.
Yeah, this will be very basic question, definitely. You have shown some formulation of potentials. How does it look like?
This one?
Yeah, there are others also. You have taken some potential.
Yeah, this is the late time potential,
Yeah.
which gives us the cosmological constant. I'm happy to elaborate more if you want, but this is the brain anti-brain potential.
Yeah. How does it look like graphically?
Sorry?
স্যার আপনি কথা শোনা যাচ্ছে না মাইক্রোফোনে
Oh, sorry. How does it look like graphically?
We have not plotted it out. It's a scalar field potential.
It doesn't matter. Thank you. Doesn't matter. You will do.
Yeah.
Fine. Thank you.
Any more questions? So, okay, I have a question slash comment slash criticism. I mean, if I understand correctly, inflation was invented to kind of, get away from, to solve some problems in Big Bang theory, which required very fine-tuning initial conditions.
Yeah.
So here you are trying to reproduce inflation by making a brain anti-brain potential, which is living on some throat on a Calabiao, if I understand. Now that is a very, very special and artificial initial condition. So this is my criticism of string inflation, is that instead of you're just replacing a very nice problem, a very nice solution by a very unnatural construction from string theory, because there is no explanation in this scenario why the brain and anti-brain was facing each other like two cowboys.
Can I comment on that? Yeah. Okay. So there's actually two. I'll give you 2 points why I'm personally interested. One, it's sort of like the reductionist approach, I would say, in the sense that, for example, when we were studying quantum field theory can allow solutions. For quantum field theory you can write quantum field theories which do not describe our universe, right? So we are trying to apply a method, or we are trying to understand which are the cases that gives you inflation, and this warped type, as you know, this Klebanov-Strassler or this warped type scenarios not only solves this inflation problem, like you can have this inflation and blah, blah, blah. And even if you start like in the bulk, higher up in the bulk, the brain and brain will attract and come together. And second point is that, so the first point I would like to elaborate is that in this approach, we are trying to understand the regions where you can have inflation, or where you can standardly realize this early universe mechanism. One. And then number two, so for example, one of the attractions of this is that experiments are actually telling us that look at this kind of potentials. These kind of potentials, usually without doing a string theory way of doing things or a quantum gravity way of doing things, it breaks the naive effective field theory analysis. So these kind of methods require a quantum gravity treatment. I am happy to talk more to you later.
Maybe it's time to go for that. Is the tea break or yeah? Oh, so is it the? Oh, okay. Yeah, there'll be an announcement now. Oh, let's thank Raki.
We are almost at the end of the 4-day conference. I think we'll be having a very short closing ceremony. And I would like to invite the convener of the conference, Professor Supriya Shaha, and the organizing secretary, Professor Mohammad Kamrul Hassan, to come on stage. I'll also invite Professor Alamgir Kabir to come on stage. So we will be handing over the certificate to the poster presenters, and I'll read the name, and please come to the stage. M.A.A. Mamun, not present? Please raise your hand first. Farhat Tasnim. Mohammad Zakaria Hussain. Shahadat Zaman. Farhan Noor. Please come on stage. Humaira Binte Awal. Please come on stage. Abdullah Haq. Abdullah Haq. Acha. Debushree Roy. Arafat Rahman. Fahim Parvez. Najmul Islam Tanveer. Shahbaz Khan. Said Shobhon. Mahbub Mahin. Suparna Bishwash. Arifuzzaman Razib. তাপসচন্দ্র সাহা, অর্পিতা দাস, তাসনিয়া ফাইরুজ হাসান, অর্পিতা দাস, তাসলিমা সরকার, মোহাম্মদ মহিউদ্দিন, মুসাম্মদ দিল আফরোজ, মোহাম্মদ এনামুল কবির, মহসিনা তাইয়েবা, সুরিত সায়ন্ত, এম এম হুসেইনা, কাজী আবরার ইবনে আমিন, হারুনুর রশিদ, মেহেদি হাসান জিহাদ, মোহাম্মদ হাসিবুল হাসান, মোহাম্মদ সজীব, হুমায়রা বিনা, এস এম খুরশিদ আলম, মিনাজুর রহমান, নূর নবী, মুসাম্মদ ইশরাত জাহান, তাহমিদ হুসেন, শাইফুল কবির, রিয়াজ শফকত, তাহমিদ হোসেন, সুজয় দাস, হাসনাত মোহাম্মদ নাইম, সঞ্জিদা তনজিদ, সালাউদ্দিন সৌরভ, মাহিদুল ইসলাম সুমন, কানিস ফাতিমা, মজহারুল ইসলাম,
মোহাম্মদ নাইম,
কি সালাউদ্দিন সৌরভ, সালাউদ্দিন সৌরভ, ওকে, আচ্ছা
সালাউদ্দিন, প্লিজ।
আপনি এখানে চলে আসেন।
ওকে, তোমার নাম হাসনাত মোহাম্মদ নাইম। আচ্ছা যাও দিয়ে দিবি।
I am now inviting Professor Mohammad Kamrul Hassan to say a few words.
So, these 4 days definitely was a tiring, but we passed that. Thank you very much for coming and attending this conference. In fact, I cannot thank you enough for taking the pain, our guest who came, who took the pain to come all the way from India, Pakistan, Nepal, USA, and we also had speakers online Nobel laureate Phillips, Joe, and Ueda. We have one special guest from, I forgot, from Brazil, Hilda. Thank you very much. Also, all the participants, local participants. And I would like to specially thank my co-organizers who helped me, who worked so hard to make it happen. It would not be possible without saying thanks also to the sponsors. So I tell you, I just mentioned the names, some of the names. Our Ministry of Education boards, they supported us. Nurul Alam, DG of Novo Theatre, one of my friend, Masudur Rahman, BD Auto Industries, PD of RNPD, PP, Ispahani, University Grants Commission, Sunnydale School, Architect Faizullah, Shahjalal University of Science and Technology Alumni Physics Department, Chairman of Bangladesh Atomic Energy Commission, Superstar Group, Dean, Science Faculty, Professor Ishtiaq Sayyad, our colleague, Professor Jahid Hassan, Director of Rupur Power Plant, Donatella Cheska, my wife, Paragon Ceramics, Janata Bank, Agroni Bank, Sonali Bank, BSMMU, our own alumni, administration, Hotel Intercontinental, and many others. Thank you very much. It would not be possible without your support, financial support actually. And last but not the least, I would like to invite the convener of the organizing committee to say a few words. And before I leave, I once again thank you very much.
Good afternoon. I think everybody is tired enough and not like to listen anything, but still formalities are there. So I would like to first thank the local as well as foreign participants. Thank you very much. I think you have taken enough pain to come to the Bangladesh, but still to make this conference a success, we need you. So thank you very much. And this conference would not have been possible without the effort of the Department of Physics, my colleagues, and the Bose Center for Natural Studies. Especially some of the colleagues, my colleagues in the Department of Physics, they worked so hard. They worked so hard. Without them, it would have been impossible to make this conference. So I thank you all very much. And at the same time, there are several sponsors. And most of the encouraging thing is we get the response from every part of our society. That is a pleasure for us. So thanking you all again. See you soon, hopefully. Thank you.
May I have just a word? Excuse me, may I have just a word?
Sure. Just 1 minute. Let me, yeah, you will have 1 minute.
Yes.
I forgot to mention one thing. I started with the donation from my students. I think this is the first time that a conference is initiated by the donation from our students. So I must thank them first. Thank you. Also, we had a group of volunteers, I forgot to mention them. They worked so hard. It would be unfair not to thank them. So thank you all so much. who are working so hard. In the middle of the night, they had to go to airport to pick them up and did all the things. So I'm really, 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 really thankful to you. Thank you. And now, okay.
On behalf of all the participants, I'd like to express our deep appreciation of all the organizers for the academic program, wonderful hospitality, and a feeling of being taken care of in a most friendly, loving, and warm manner. Of course, in particular, Professor Kamrul Hassan was our contact point. So my gratitude to him is infinite. But as soon as I landed here, until the time I am preparing to leave, I am touched by the help received by all the organizers. And last but not the least, I would like to echo Professor Hassan's statement, saying that the young volunteers who have literally shadowed each of us right from the moment we descended at the airport till the time we are preparing to leave, I found it incredible, and I found it incredible to believe that they could put in so much of effort on their own. So my big support, please give a big hand to everybody. Thank you.
Please, Professor Talab.
Actually, I just want to echo what has just been said, but I also want to say that I'm going back with very, very positive feelings of what can happen at Dhaka University, and the conversations, particularly with the students, have been really rewarding. And I think, you're all off to a fantastic start. I'm sorry I haven't been here for a while, but I hope to come back, and I think my other colleagues who are here will also like to come back. It was really invigorating, and I think just the quality of physics that is going on and the enthusiasm with which people are involved in other activities was just very heartwarming. So it was fantastic, and thank you very much for inviting us. It was a wonderful occasion.
Hello. Yes. For me, it's a trip of great emotional, how should I say, matter, because it is here that Professor Satyendranath Bose did his famous work, and I had this tremendous opportunity to have known him, and I am really grateful to all of you, the organizations or organizers, for remembering me and giving me an opportunity to be present here. Thank you ever so much. I will convey my feelings, which are entirely positive, to the family.
I'd like to say something. So as I mentioned during my talk, I should elaborate a bit. So since last 4 years, Kamrul is really telling me, Shyamalda, we should do something to celebrate Bose-Einstein statistics 100 years. Besides that, I would like to add, Kamrul, with your permission, he has a dream of building an institute here by his name. So he's been telling me into my ears so that I spoke in a different language in Bengali. But at least I could see that he could organize this celebration of 100 years. This is the footing step. I think therefrom we have a platform to jump on, I think. Thank you, Kamrul, for your efforts. And also the students. Kamrul was my only friend here in Bangladesh. Now I have many friends. I don't want to mention each of them, but you understand whom I mean. I have many friends among the faculty, also students, among the students, boys and girls. So thank you very much. And I always love to speak in Bengali, tempted to speak in Bengali. But sorry for the international faculties, I have to really speak in English, which I'm not good at. Thank you very much for everybody.
I have one comment. During the organization of this conference, we did many mistakes. So I apologize for that. But the good thing is we learned a lot from these mistakes. Okay. So I am now actually inviting the organizing committee members to come on stage. We will be taking a photograph.
Yeah. Good memory.
Please.
How? Okay. Of this audience?
With a volunteer.
Please come on stage, all the volunteers. Please.
Achha, volunteers.
Hello. In my little life, I could have never imagined that I will be in here among you, serving as a volunteer in this event. And it's been a wonderful experience serving you people, helping the guests come here, get to the hotel, help them reach airport, and everything. I can say on behalf of the volunteers that everyone enjoyed every single part of serving you people, helping you in every ways. So it's been an honor for us, actually. Thank you.
Participants, if you like to take tea, please proceed to the cafeteria at the first floor. Thank you.